Okay, now the live stream is live.
Sorry for the noise.
So I think we can start, no?
All right, if that's okay, I'll start. Yeah.
Oh, no, I just had to introduce you first. So welcome everybody for this session about random number generator. So we will have 3 talks, 5 minutes each, and then we have 15 minutes time for discussion. So we start with a presentation by Thibaut Michel, and he's presenting a work which was made by an international consortium from Australia, Italy, and France. And it's about real-time self-testing quantum random number generator with non-classical states. Please, Thibaut.
Thank you. Before I start, let me just thank Christian, Serge, and all the other organizers for this conference and for giving me the opportunity to give this talk. Also, it's my first online conference, so I think the organization was really well done. All right, so I'll present this experimental work that's been done at the Australian National University. And it's on a real-time self-testing quantum random number generator with non-classical states. So let me start by explaining the protocol. So this falls into the category of semi-device independent QRNGs. And semi-device in that we don't trust the source of entropy of the QRNG, but we trust the measurement device. And so the protocol is as follows. We'll randomly measure either X or P, these 2 POVM, that corresponds to 2 conjugate quadratures of the state. And delta X, delta P refers to the precision of the POVM measurement, and K is just for labeling the bins. And the idea is that by measuring the P quadrature, we'll be able to estimate a bound on the mean entropy of the conditional mean entropy of the X quadrature, which quantifies how much true random numbers you can extract from this X measurement. And this is done with the entropic uncertainty relation that relates the mean entropy of X and the max entropy of P. And this C here is just a constant that depends on the maximum overlap between the 2 POVMs. So with this, you can form this lower bound that just depends on measurement of the P quadrature. So then when you measure P, you get this estimate. And then when you measure X, you can extract a secure random number from that. So the assumptions of these protocols are that we trust the measurement device, as I said, although you can afford to not trust the classical noise, because you can take it into account as as mixedness of the input state that you measure. And then the assumption on the source, there still remain an IID assumption for estimating this max entropy. And also you have to assume that it's bounded, this source, because the entropic uncertainty relation only works for P of M that spans the entire phase space. All right, so here's another scheme of the protocol. And the main feature is that everything was done in real time. So the data acquisition, the entropy estimation, the hashing. Also, we had this active quadrature switching. So the local oscillator was alternatively locked to X or P and randomly. And we also had some mechanical beam blocks to measure shot noise and dark noise. So this whole QRNG was self-testing and self-calibrating in that sense. And we ran it with a non-classical source, so squeeze state of light, and show that it improved the amount of randomness that you can extract. So to start off with, we tried some thermal state source that we generated with phase and amplitude modulators. And here are the results. So we run the protocol, and I'll show on this graph. So the blue line here is the theoretical estimate of what the bound should be for a thermal state with a given variance. The red line is the unconditional mean entropy. So that's the amount of randomness you would extract if you trust the source state. So if you assume there's no correlation to malicious third party. And then the dashed line is just a simulation of the theoretical low bound for if you take into account the finite sample size. So in other words, the bottom line is trusted randomness and the top line is the untrusted randomness. So we run the protocol, and at some point we estimate this lower bound and find this value here for a given thermal state. Then we'll go to the other quadrature, extract random numbers, and then estimate again. And so we have this cluster of points, and then we run it for several different types of thermal state with different variants, and this is what we get. So this sort of validates the idea behind the protocol, is that when the variance of this thermal state increases, the apparent randomness in the signal increases, as you can see with the red line here. But the amount of trusted randomness should decrease because the amount of noise you see could be just correlated to a third party. And then we ran it with the interesting state, which is the squeeze state source, which was generated with OPA cavity. And the idea here, as opposed to the thermal state, is that since you have some squeezing in one variable, so you can measure noise on the peak quadrature that's below shot noise, then this is a guarantee that there is some anti-squeezing noise on the other quadrature that's not correlated to any third party. In other words, measuring squeezing is a sign of purity of the state, if you wish. So the more squeezing we have, the more randomness we should be able to extract. And so that's what we did. We ran the same protocol with this source and a different amount of squeezing. As you can see, when the squeezing increase, we get to better entropy rates. The unconditional mean entropy is still higher here because there's some impurity in the state. And so if you have squeezing, you can increase the amount of randomness that you have. All right, that's basically it. So we demonstrated real-time self-testing QRNG based on non-classical light. We tested with different sources. And oh yeah, I forgot to mention the speed of this QRNG was quite limited. It's only like tens of kilobits per second. But we didn't really focus on speed since we are limited by the bandwidth of the squeezing we had anyway. But you can reach gigahertz by using a dedicated hardware for hashing, broadband squeezing, which now is available, and optical beam switching. And also this device can be miniaturized with on-chip squeezers and chromaline detections.
Okay, thank you very much.
All right, thank you.
So let's switch immediately to the next speaker. This is Jing-Yan Ho, and he will present his work on benchmarking and quantum random number generator with machine learning. Please. We can't hear you.
I think he is still muted.
Yeah, I don't know how I can. I know how to mute people, but not
now that should work.
Okay, please go ahead.
Okay, so yeah, so thanks for the introduction. So today I'll share with you our recent work benchmarking QRNG with machine learning. So this work is done with my ANU colleague Asad and Pinkoy, and also ML expert Omid and Nan. So consider a case in 2012 where a widespread of vulnerable keys are discovered, in particular by exploiting the entropy loopholes. For example, poor entropy sources, non-eligible amounts of the private keys are actually compromised. So this tells us that if you have a weak RNG for your crypto system, you are essentially leaving a backdoor to your supposedly secure system, as cryptography is only as secure as its weakest link. So this is what motivates us to use quantum RNG, where we can use the inherent quantum randomness in the device. However, as we have heard from ID Quantic talk from Felix on Tuesday, in reality, the state might not be pure, and neither do we have a noiseless measurement and environment. So as such, a QRNG must be characterized and also modeled properly to ensure that only the trusted entropy are extracted. So nonetheless, in practice, our device might deviate from the original modeling, such as unaccounted noise, residual correlations, or even wrong assumptions. And furthermore, imperfections from the extractor, such as an overly simplified post-processing or poorly chosen and extractor seed together, all this could lead to a not so uniform output. So as such, with the advent of big data and machine learning, it's not hard for us to imagine that an adversary can use such a technique to compromise the security of a QRNG. So there are, of course, methods such as health checking, entropy estimation, and statistical testing. However, it's reminded that all these methods are based on finite sets of statistical elements, and they could lead to, and they are also prone to unknown statistical behavior and also correlations. So this begs the question of, can we examine the underlying randomness without, say, opening out the box or without using a statistical approach? So in our work, we answer this question by turning into this adversarial tool of machine learning into a diagnostic tool. So the method we are looking here is, can we learn from the previously generated random numbers to predict the next output bit? So to do so, we train our deep learning model over a training set, and then we evaluate its performance over several test sets by comparing its accuracy PML with respect to the probability of most frequent values of, let's say, a training set, PG. So the key components of our deep learning models are as the following. First, we have the CNN, convolutional neural network, which captures the spatial information from adjacent inputs. So for example, with multiple convolutional layers, more high-level features can be reviewed. RNN is, on the other hand, can help us to capture the temporal information from a sequence of input. However, in practice, useful information can be too far away from the present, and RNN might have difficulties to do so, to remember it, just as human. So we use a long short-term memory to help RNN to deciding what to remember and what to forget. So we test our idea upon a continuous variable QRNG, where the entropy source comes from homodyning the vacuum fluctuations. With the dynamical range optimized, our RNG is secure against classical sign information and so on. So we now let's look at the result. First is the entropy of the classical with classical origin by turning off our local oscillator of the system, and the second is by turning it back on. So in the interest of time, let's just look at the case where the simple estimator of this PG max bin guessing is most different from the machine accuracy PML. So we see that by plotting, let's say, the power spectrum and the autocorrelation of the data, we see there are strong periodic traces and also some persisting autocorrelation. And in fact, the stage in our QRNG is actually a stage without low pass filter, where the aliases are still present. Hence, our machine learning attack utilizes these features in predicting the next bit. So finally, we also have a test where we put pseudo RNG and the quantum RNG side by side over both the statistical needs test and also machine learning benchmarking. And we see that there's an interesting feature here where for the CRNG, a congruential PRNG with a period of 2 to the power of 28, it actually passes the needs test, but it didn't pass the machine learning test. So in a sense, it couldn't hide on true identity under the scrutiny of machine learning. So to sum up, you definitely need a good RNG for your cryptography, be it classical or quantum. And to this end, we put forth our ML benchmarking tool, where a designer can use it to diagnose the QRNG rigorously, and a verifier can also benchmark the raw and post-processed data with an algorithm-agnostic manner. And finally, for an end user, they can just test the entropy of their device with minimal system knowledge. So our code is also available on GitHub. And as promised in our longer version of the talk, we also have a tutorial version on Google Colab, which can be accessed here or talk to me later. So yeah, thank you for listening, and we will be glad to interact with you all later on. Thanks.
Thank you very much. So before we switch to the next talk, I would like to remind the audience that you can ask questions now by using this question and reply function. So please don't hesitate to ask your questions there to any of the speakers and indicate to which speaker you would like to ask a question. Okay, so now let's go to the next talk. It will be given by Fabian Beutel from University of Münster in Germany, and it's about broadband detector integrated QKD receiver chip for gigahertz clock rates. Please, Fabian.
Yeah, thanks for the introduction. I'm from the group of Wolfram Pernice at Münster University. On this conference, we've already seen quite a few talks on integrated QKD with impressive work. However, most of these works or the chips are actually focused on Alice, so on the sender side. And we actually also wanted to bring the benefits of integrated photonics to Bob. And the benefits, of course, are that you don't need to worry about alignment anymore. Also that it's much easier to stabilize a small chip, which is only very small compared to a big bulk setup. And finally, of course, most of the scalability issues disappear once you move from bulk setups to integrated fabrication process. And for integrated QKD, it's always very nice to actually work with time-based protocols or time and phase-based protocols. And for our implementation, when we actually built this chip, we designed it for these time protocols where you actually need to somehow check with interference. You need to do some form of interference measurement, so you need this Mach-Send interferometer. And for our implementation, we actually chose this 3-state protocol presented by Hugo's group in Geneva, I think 2 years ago, where you basically have 2 bases, so the Z and the X base, and only 3 states. So you use the early and the late time bin and then the superposition state. And only this Z base is used to transmit information, and the X base is only used to estimate the phase error rate. This is relatively simple to implement, so it's a very nice protocol. And basically what you need is you need a splitter and then this Mach-Send interferometer, and then of course 2 detectors. And this part with the interferometer has also been integrated by other groups in the past. I think the O'Brien group has showed something in this regard a few years ago already. However, we also wanted to integrate the detectors on chip to really have one integrated package with everything on one chip. You also heard at this conference already that SNSPDs, so superconducting nanowire detectors, are basically state of the art with regards to single photon detection. And they have really matured in the past years. So they offer great detection efficiency, also really low noise. And just recently also people have shown a jitter of below 3 picoseconds in the lab at least. So this is really a very mature and promising technology. But when you, of course, what you have traditionally in this SNSPDs is this meander nanowire, and the light is incident from the top in this picture. And this is, of course, very difficult to integrate on chip. So what we use in our group is a slightly different technology. So we start with a waveguide here in blue in this picture, and then we just place this U-shaped nanowire here in red on top of this waveguide, and this actually absorbs then through the evanescent field, absorbs more or less all the light in the waveguide, depending on how long you make it. And this, of course, then allows you to add additional photonic elements in front of this detector. So it's perfect for photonic integrated circuits. And also it has the additional benefit, and this is also something Felix talked about in his talk, that one challenge for QPD is to make these faster, these detectors. When you actually have this design, you can actually, they are intrinsically faster since the wire doesn't need to be so long. So usually we have about 5 nanoseconds dead time. And you can even make them very short if you only use like a bow tie setup. And in this case, up to 2 gigacounts per second have been demonstrated by our group in the past. And so this all we integrate on our chip, which as a 3D rendering looks a little bit like this. So we have basically only one input that comes from Alice, and for the coupling from the fiber to the chip, we actually use 3D printed couplers. So this is really 3D printed onto the chip after fabrication, which is nice because it allows vertical coupling. So we can really address the whole surface area of the chip, which allows for many channels in principle. And also it's very broadband. So with this couplers, we can really couple in light from the visible all the way to 1600 nanometers. And then of course, it depends on the waveguide that you build. And then we couple most of the light we forward to the main SNSPD, and then about 10% is put into this MZI. And of course, if we talk about 200 picoseconds delay, this corresponds to 3 centimeters on silicon nitride. This isn't really long for fiber optics, but if you move to integrated optics, this suddenly becomes this huge delay line. And although we're on a low loss platform, we have some losses if you have such a long delay line. And this we balance out by adjusting the input splitter of the MZI. And then finally, we have the output where we measure the destructive interference with the secondary SNSPD. And this is what the chip looks like. So this is an SEM picture. And then here on top, you have a photo of the chip in real life. So you can see that we can place about 50 to 100 of these devices on one chip, which is about 15 by 15 millimeters big. So with this, we actually performed the experiment, and we kind of compared it to this implementation by Hugo's group. And we can see that for short distances, so for short small channel attenuations, we don't actually suffer from this dead time that APDs bring with them, since the dead time is really not really limiting us here. So we're not really saturating the detector, which is nice. In the long distance range, here the setup from Geneva is more sophisticated since they have a lower error rate in the state production. But here mostly we're limited in the state preparation. For us, it was really a challenge to get a good extinction ratio on Alice's side of the setup. You can also see that at least in the Cuber, we're not really limited by dark counts, so this is relatively stable. Whereas in the phase error rate, where the counts are of course much less, you can see an effect of the detector count rates from about 25 dB. Then finally, maybe. Sorry, I can go back. No, thanks. Okay, then let me just end with this. I think that's over time anyways now. So thank you for your attention, and yeah.
Thank you very much. Thank you to all speakers. And now we can go over to the questions, and this will be handled by my colleague, Felix. So
yes.
Felix, you collected the questions, so please go ahead.
Yes, we got some questions. So yeah, thanks to the speaker. All great short talks. Now we have time to dig a bit more with questions. So first of all, there's a question by Christian, actually, for Jinyang. The question is, have other groups already used your machine learning test for their RNGs? Has it been used by others?
Yeah, so there are requests for the codes questions, but I think so far we haven't seen a publication that directly uses our code. There are publications that uses techniques similar, but exactly so not yet. Yeah, we are looking forward to it.
Okay. Yeah,
I guess it could also be interesting for classical RNGs.
Yes,
you know?
That's right. Yeah, so in fact, that's what we are also targeting at. Yes.
Yeah. Okay.
Okay, so we have another question from Gong Zhang, which is for Fabian. He's asking about the yield and the fabrication time for such a 3D printed coupler. How difficult is that part to make in practice?
So the machine which we use for this is a NanoScribe. This is a commercial machine that you can just buy off the shelf. The fabrication time per coupler Right now, it's about 5 to 10 minutes, really, so it's not super fast, but it can be, so you can speed it up, and there's some work going on for this. And the yield is relatively high. So there's you need some testing structures usually on the chip itself, where you start to finding the right parameters for the chip. But once you've found those, the yield is actually rather high on the chip itself. Right, I can't give a precise number for the yield for the couplers right now.
Okay. So actually, Thibaut has a question. So for you, Fabian, he's asking, what's the material of the 3D printed coupler?
So it's some polymer. So it works by 2-photon absorption. We have different polymers actually that are used. So I would have to look up the exact polymer that was used here. Yeah, in principle, I can send you some link to a paper if you like. Then.
Well, maybe just a follow-up question from me on this. Do you have problem with polarization with this, or do you have to control polarization?
Yes, so not due to the couplers. So the couplers are really not very polarization sensitive, but of course the waveguides are. In our case, we usually are limited to the fundamental TE mode in one mode only. So we always only work with one polarization, and therefore we are also polarization dependent. But in principle, you can make also your waveguide higher and support two modes. And then, of course, you need to adapt the nanowire design a little bit. But in principle, this can also be done and designed in a way that you're not very polarization dependent anymore. So the couplers here are not the limiting factor, but the waveguide usually is.
Yes, okay. Which is in silicon nitride, right?
Yeah, we're working with silicon nitride.
Yeah. Okay, so I have a question for Thibaut. So yeah, okay, yes. Thank you for muting. So I'd like to learn more about the miniaturization challenges that you might have with your system. If you wanted to miniaturize, it's a CV or it's a CV-based QRNG. Is everything easily miniaturizable, or you have some parts that you think are definitely challenging?
Well, yeah, of course there are some challenging parts, that's for sure. But it's just a perspective to have. But yeah, it depends whether your detection is in free space or if you manage to integrate that as well. And the amount of loss that you include with the coupling. But so one of the main thing is that when you have on-chip squeezers, which, well, are not easy to make, but they are intrinsically like broadband because they're usually not inside the cavity, which makes them like more efficient if you use them in such protocols, because then you're not limited by the bandwidth of your squeezing. So I think in that case, it's interesting, yeah.
Okay, thank you. Okay, so we have more questions from the audience. There is a question by Roger Colbeck for Jin Yang. The question is, okay, let me just read it through.
Well, I think Roger can ask the question himself. He's already almost connected. So
sure, yeah, good idea. That's true, he's right there.
Yeah, so you showed an example where your method detected correlations where the NIST tests do not. So I think that was based on a random sequence that had some very long repetition rate, if I understood correctly. So I was wondering, what about the converse? So are there types of imperfect randomness for which your machine learning algorithm does badly or can be outperformed by other tests, for example, the NIST tests?
Yeah, I think that's a very excellent question. So we believe that, so if we look at our method, we are actually having a training set coming from the random number generator. So that means, in a sense, our method is actually agnostic to what the types of randomness inside. So that means we are actually depending. Yeah, it's not input depend. It's not a fixed method, but rather it can adapt according to the type of let's say imperfection coming from the random source. So in a sense, we believe it can probably, it should be able to learn. But what type of randomness that our method might does badly, I would say could be, for example, if the range is so long that and the training data is not large enough to cover that correlation, then that could be what might happen. So for example, in the slide that I showed, for one of the pRNG, pseudo-RNG, we actually didn't crack it. And that's because the data size is almost the same size, or if not larger than the training size. Yeah.
Great, thank you. So another question from for Jinyan by Nirai Kumar. So I will, yeah, he's unmuted. Great, Nirai, please go ahead.
Yeah, hi Jingyan. So my question is like, does your results imply that QRNG is like robust to deep learning attacks? Like, because in one of the plots you had like the probability of guessing was the same as the probability that the machine learning model was doing. And the second thing is that like, have you also explored like other neural network structures? Like, do you expect like better performance of the ML model? Like if let's say neural network is denser, or if you consider some other structures?
Yeah, thanks. That's also a very good observation. Indeed, our QRNG itself, I would say here, as I also show in the slide, your QRNG is usually imperfect and there are noise. Your extractor might not be perfect, so on. So I would say when you by robust, that means if you have done everything properly. So yeah, it's a good test in that sense. So in fact, also throughout my slide, I also show that if there's some hardware that you didn't design properly, so your raw data might have some correlation before the hashing, and it might also screw the final output. And as for whether the ML performance can get better, so there are actually, if you had a chance, you can have a look at our tutorial or the GitLab, and there are a lot of parameters where you can play around with for the machine learning. So for example, here I didn't explain about the step size, so you can also tune the overlaps between the learning, such that if it's denser, usually it will be more accurate, but at the cost of longer training time. And it can take, let's say, half a day or so, depending on your hardware. Yeah.
Great, thank you. So it's 11:30. I think we don't have any more questions from the audience. So Hugo, would you be okay with finishing now?
Indeed. Well, I have a few questions for Fabian, but I think I can ask him the questions at the coffee break. So I think indeed we can close this session. Thanks again to all speakers and for the discussion. And we meet again in 50 minutes. Okay, I'm back from a coffee break.
Yes, I was wondering if you everything was going to be on time, but you are. Okay,
hello, so Tobias. Hello, right, guys.
So we're live now. Okay. It's 11:45, so let's start our session. So our session, this is 30-minute session. We're gonna have 3 speaker slots, but the last slot is going to be 2 speakers. Without further ado, I'd just like to start right away. Let me just bring up the schedule, and then our first talk is by Gong Zhang. Let me just check. Do we have? Sorry, I'm lost in the windows here. Oh, there it is. Okay. Our first speaker is Gong Zhang. I'm sorry, I just trying to bring the window back and somehow I have lost it. Yeah, the hazards of online conference like this. Okay, got it. Okay, great. So Gong, please go ahead.
Okay, hello everyone. Thank you for joining my talk. My name is Zhang Gong from National University of Singapore. Today I'm glad to be here to introduce you one of our recent work entitled Securing Practical Quantum Cryptography with Optical Power Limiters. So let me start the story by showing you a lot of practical attacks into a QKD system. And simply speaking, we can characterize them based on the target, either receiver or the source. But for the transmitter, luckily we have the MDI QKD, which could close the detector loopholes. But for the transmitter side, we still have to find a practical and secure way out. And power limiter or energy bound is one of the important tools. One main application is to solve the Trojan horse attack problem. So for Trojan horse attack, in a QKD system, if could inject a strong light into Alice equipment and collect the reflective photon with the encoded information, it is dangerous and couldn't be detected by just looking at the error rate. So there are a few previous works to counter such attacks, and the basic idea is to limit the amount of unauthorized input power. And another field requires energy bound is the semi-DI QKD or QRNG. And as long as we can trust the energy bound, the QKD or QRNG will be secure. And again, a power limiting device is very important here. There were a lot of previous work that could provide energy bound in an optical system. One could depend on the fiber damage or just use a filter. And another type would be based on the nonlinear effect, like two-photon absorption or thermal optical defocusing. And here our power limiter is mainly based on density effect because of the relatively low threshold and the simple design. This page I show our power limiter design. We have input-output fiber as the interface, and we have a pair of collimators to collimate the light, and an active medium with negative thermal optical coefficient is put in the optical path. And here we choose acrylic. And the input laser will heat up the center of this material, which could reduce the refractive index here and make the prism look somehow like a concave lens. And then if we put a diaphragm here, we can control the received power. And a filter here could be introduced to prevent wavelength attack. And we provide more detail on the full length video online. So basically that's it. All we use is the off-shelf components to provide robust and cost-effective design. And in this page, I show we show the power limiting function could by both the simulation and experiment. In this figure, you could see at first, the output power will just increase with the input. And after a certain threshold, the output will start to decrease. And by changing the prism length or the diaphragm width, we can either shift the curve or change the shape of the curve. And also we consider other degree of freedoms, and I won't go into the detail due to the time limitation. So basically here we prove that the power limiter is also working for pulse laser. And this page we show that we notice the wavelength dependency of such power limiter only comes from the material absorption spectrum. So that is why a visible filter could also help. And for laser damage attack, we provide a solution by using the reflective structure like this. And finally, I will introduce you one of the main applications of such a power limiter, plug and play MDI QKD. The system will look something like this. The advantage of plug and play MDI is that the user doesn't have to purchase expensive laser and detectors. And with a common laser source here, the wavelengths could be identical for both Alice and Bob, and the clock synchronization will be much, much easier. But the main issue prevent the application for being used is the Trojan horse attack. And that is why we need to put a power limiter here. And we did a simulation here shows that even if we consider some average Trojan horse photon leakage, we are still able to bound the information without much compromise on the total performance of the system. Yeah, so as a conclusion, I would say this is, to the best of our knowledge, quite complete analysis of such a cost-effective passive power limiter. And still, we are open for advices from you and collaboration on this work. And I would like to thank Professor Charles Lim and Professor Gong Xiu and all my colleagues for their contribution and support on this work. And thank you all for the listening.
Yes, unmute. I was muted. Thank you very much. So thank you very much, Gong, for your talk. So let's move on to the next one by Tobias Garing, who's going to tell us QKD and machine learning. So another talk with mixing machine learning and QKD or QRNG. So
thank you very much. Yeah, I'm happy to present our work here at QCrypt about a continuous variable QKD implementation using machine learning. So let's directly jump into it. This is a schematic of our QKD system. We have a transmitter on the left, a receiver on the right, and quantum channel in the middle. We use a continuous wave laser in the transmitter station and an in-phase and quadrature modulator to generate coherent states with a Gaussian modulation. On the receiver side, we implement a heterodyne detection, so we measure amplitude and phase quadrature at the same time using a technique called radio frequency heterodyne detection. So we just use a simple single 50-50 beam splitter and then a local oscillator laser that is frequency detuned to the transmitter laser. And in that way, we can actually measure both quadratures at the same time. Our laser at the receiver is free running to the with respect to the transmitter laser, and therefore phase compensation is very important. So if you don't do any phase compensation, then the correlations between the symbol we measure and the symbol that was modulated is very bad, and that is roughly what you can see on the left. So we actually have to perform phase compensation, and we do this by also modulating a so-called pilot tone onto the light. So the pilot tone is a sine wave that is frequency multiplexed to the quantum signal. And what you see here is a typical receiver spectrum. So you can see here on the right, this is the beat between the two lasers. It's about 200 megahertz. The x-axis is missing here. So this is the frequency detuning. Then we have the quantum signal sitting here and a pilot tone that we then measure, and we estimate the phase of this pilot tone to actually compensate the phase of the quantum signal. The trick is now to do this phase estimation in an optimal way, and our method uses a Bayesian inference approach based on an unscanted Kalman filter. So Bayesian inference is a well-known technique for parameter estimation from statistics. And what you need for this is, for example, the prior information. Prior information here is about the laser noise, the laser phase noise. And this is a problem because, well, a perfect laser follows a Wiener process, but nobody has a perfect laser. So we actually do not really know how this this phase noise model looks like. And this is what we are learning from the data, so that we do not need to know it in advance. The second problem is that usually Kalman filters work for linear systems, but our system is actually non-linear because this is the pilot tone, well, it's a sine wave, and this is the phase here we want to extract. So there's a sine relation between, and we have to deal with this non-linear system. And this is what the Kalman filter does. And it does it by approximating the posterior probability distribution by a Gaussian. So the posterior probability distribution is what the Bayesian inference approach is estimating. So we estimate that by a Gaussian. And then we propagate actually the mean value and plus minus the standard deviation directly through the nonlinear system. So we do not linearize that system. And these are our results. So here on the left, you can see the pilot tone signal to noise ratio. This is basically how much power we have in the system, how much we filter the system. And on the x-axis, you can see the excess photon number. This is basically the figure of merit for a QKD system. And what you can see here in blue is the excess noise we achieve by using our phase compensation algorithm, which is very broad for the signal to noise ratio, so it doesn't really matter what to choose. And we compare that to mainly the reference method, which is basically just taking the Arcus tangents between the amplitude and phase quadrature values. And for very high signal to noise ratios, they converge, they work equally well. But in our case, we can actually use much lower power in the pilot signal than is otherwise possible. This translates into a secret key rate. It's just basically 1-to-1. And with this, I would like to summarize. So we can show that using our technique, we have good performance over a large range of signal to noise ratios. That means we are very robust against environmental changes. And it works also in the low signal to noise ratio regime, which has implementation advantages because we can really use very low signal pilot tone powers. Thank you very much.
Great, thank you very much, Tobias. So before going to the next talk, I remind you that you can ask questions anytime using the Q&A feature of the Zoom, so please go ahead. And then with this, we're going to move on to the next talk, which is 2 talks merged into one by Wei Luo and Kai Lun. So please go ahead.
Okay, thanks, Chair. Hello, this is Wei Luo from Nanotechnological University. And today, my colleague Saling and I would like to give a brief introduction on our work on chip-based QKD system. And first, in the first part, I will present our recent progress on the integrated chip platform for measurement in device-independent QKD. As we can see in the recent years, more and more researchers have been involved in the studies of embedding quantum photonic applications into scalable integrated devices. And the technology of integrated quantum photonics has enabled the generation, processing, and detection of quantum state of light in a small chip at a steadily increasing scale and level of complexity. Until now, a range of optical waveguide platforms have been developed for the integrated quantum photonic applications. Among these platforms, in our opinion, we believe that silicon photonics is an optimal choice for QKD because it can provide the most mature solution compatible with CMOS fabrication process and promise fully integrated at QKD with integration of detectors and lasers. And typical on-chip QKD demonstrations can be seen in the work from researchers of University of Toronto in 2016 and University of Bristol in 2016 and 2017. In their work, they implemented various DVQKD protocols using their chip scale transmitters and receivers. Our group has also demonstrated that silicon photonic chip platform for CVQKD in 2019. And for the further development of QKD systems, chip-based QKD systems, we are looking at the integration of MDR-QKD. We know MDR-QKD removes the detection loopholes, and its architecture is naturally suited for multi-user QKD networks. Since the most expensive and intricate component, the measurement device, can be placed in an untrusted relay and shared among many QKD users. That means each QKD user only needs to hold the transmitter, and the integration of the transmitter will greatly reduce the cost and improve the flexibility of the QKD network. Of course, the integration of MDR-QKD server is also possible. And based on these ideas, we have developed a chip-based MDR-QKD system by integrating both transmitter and the server chips. Here we show the fabricated silicon photonic transmitter chip and the server chip. And using these chips, we perform a proof of demonstration to demonstrate our feasibility of our chip scale MDI system. In the demonstration, we implemented 4-intensity decoy state MDI protocol proposed by our collaborator, Professor Xiangping Wang. And the QCrypt pulse of our system is about 2.9 times 10 to the minus 6 over a distance corresponding to 50 kilometer optical fiber link. And this result agrees well with the simulation. And we can see it is also comparable to other MDI studies, including 2 recent chip-based MDI systems. In conclusion, we have developed an integrated photonic chip platform for MDI and perform a proof of principle experiment to demonstrate the feasibility of the system. And both the transmitter and server chips for MDI have been fabricated using silicon photonic technology. And in the future, with further integration of laser diode, optical switch, and single photon detectors, and it's possible to build a fully chip-based MDI platform with high scalability and low cost. And that's all for the first part. In the next part, our colleague Cao Lin will present his work.
Hello, everyone. This is Cao Lin from Peking University and Nanyang Technological University. My talk is about on-chip time and polarization multiplex continuous variable quantum key distribution. By now, many experimental demonstration has been showing the feasibility of CVQKD with coherent states. And last year, an integrated silicon photonic chip of CVQKD based on continuous wave has been demonstrated. However, a much more practical chip-based CVQKD system based on pulsed operation and time and polarization multiplexing has not been demonstrated until now. So this work include the fabrication and the design of CVQKD chip, which includes the transmitter chip and the receiver chip. This chip is used time and polarization multiplexing, which enable signal and local oscillator light to share one channel and reduce crosstalk between them. And all the components are integrated on the chip. This figure shows the layout of our CVQKD system. The box above shows the transmitter chip, and the box below shows the design of receiver chip. On transmitter chip, we use the 3 identical amplifier modulator to generate a loud pulse with high pulse acting ratio. Here, I only show the testing result of 1 modulator. This figure shows the static pulse acting ratio. The acting ratio is up to 35 dB, and the dynamic pulse acting ratio at 5 MHz is larger than 21 dB. This figure clearly shows identical and stable light pulses can be generated in a long time. In our previous work, single polarization beamless splitter only provides about 25 dB polarization isolation. In this work, to reduce the crosstalk between signal and the local oscillator, we designed a new PBS. The testing result shows the polarization acting ratio of the new structure can provide about 30 dB polarization isolation, which meet the requirements of CVQKD system. The system noises are carefully measured. This figure clearly shows the electronic noise is about minus 83 dBm, and the the noise to the signal to noise ratio is about 8 dB. With the modulation on, the measured output is at about 12.5 higher than the short noise. So the modulation variance is about 12.5 short noise units. Now, the parameters we have measured are summarized in this table. Based on the parameters, the simulation of secret key rate under different conditions are performed. These three figures respectively shows the influence of excess noise, detector efficiency, and the reconciliation efficiency on secret key rate. This result shows our CVKT system is expected to perform well and generate a positive key rate under larger excess noise or low reconciliation efficiency. To sum up, we designed and fabricated an on-chip time and polarization multiplex continuous variable quantum key distribution system, and key components of chip and system noise are carefully measured. Finally, the simulation of the secret key rate under different conditions are calculated. In the future, we will continue to demonstrate a long-distance CVQKD using this chip-based system and generate a real key rate. That's all. Thank you for your listening.
Great. So thank you very much to all the speakers of the session. I will let Hugo continue with handling the questions.
Yes, so we have a few questions. The first is by Vadim Makarov. So Vadim, you can unmute and then you can talk.
Thank you. I have the question about the first talk about the power limiter. Do you hear me well?
Yes.
So in your MDI QKD model, do you have to input relatively high power at Alice and Bob such that their limiters stay in a saturated regime at all times?
No, for this question, no, because we just like provide an energy bound, upper bound for if how much Trojan horse photon Eve can get. So they don't really need to always saturate the polygon limiter. So it's just like a protection of fields. So everybody just working at the safe zone. But if there's Trojan horse attack coming from Eve, then the security is bounded by the power limiter, just like that.
But what would then stop Eve from just increasing the input brightness and getting a higher output brightness from Alice and Bob?
I think that's just from the output input curve we provided. It's like if you provide a higher input power, then the output will just start to drop, and it will provide us like a upper bound for the output power. And yeah, it's just like to something like that. As I don't know if I understand your question correctly.
Okay, I'm not convinced the scheme will actually protect against Eve that will use pulsed input signals at Alice and Bob, but we can discuss this in the break.
Okay, yeah. Also, I saw your second question regarding the pulse. Are you referring to that? Yeah. So if using a pulse laser, as we explained in the presentation, the security of such a power limiter is calculated by an average Trojan horse photon over like a slightly longer period. So one assumption we have is we need to operate the QKD device for a longer period, longer than the response time of such a power limiter, so that the average output power can be characterized correctly.
Okay. So maybe we go to the next question. It is by Adomas Baliuka. So Adomas, you can go ahead, please.
Hello, my question is for Tobias Gehring. From a security perspective, are there no dangers in using a trained machine learning system whose response to all possible inputs can usually not be fully qualified in a QKD protocol?
Yes, so thank you for this question. So in general, I would say that I don't see a difference between the Kalman filter-based approach we have and the reference method for extracting the phase. But in general, your question is good because the question is, can I really use a pilot tone or a reference pulse, or does that open a security loophole? I think this is still an open question that is debated. My take on this is there's no loophole as long as the additional phase noise I get because of this imperfect phase estimation is not trusted. As soon as I trust it, I open a loophole. But as long as I don't think there is a loophole by using pilot tones or reference pulses. Hope that answers your question.
Okay, then maybe let's move. Is this okay for you, Adomas?
Yes, thank you.
Okay, excellent. So then we have another question from Rupesh. I think it's also for Tobias. Rupesh,
hey, Tobias, hi. I have a couple of questions. One is compared to the phase estimation from reference pulse, what is the advantage in terms of key rate and the transmission distance if you use this piloton?
Yes, thanks, Rupesh. So in our case, in our implementation, the pilot tone power was a mere 3 times higher than the quantum signal, and for us it made basically the difference between generating a key and not generating a key at 20 kilometers. But in general, you can of course increase the pilot tone power and always achieve same performance. So in that case, it is, I would say, an implementation advantage, because if we increase the pilot tone power, well, we need more bits in our digital to analog converter, for example. And maybe there's noise spilling from the pilot tone into the quantum signal. So maybe we have to take it further apart. Or as other groups did, maybe we had to polarization multiplex the pilot tone to get to use high power. So it is an implementation advantage in that sense. But I think you can always achieve the same performance by just cranking up the power.
Okay. Okay, thank you for that. And my second question is, maybe I didn't understand much better about this one. So your pilot tone is slightly frequency offset as that of the quantum QKD signal. So in that case, the phase estimation from pilot tone, how exact that the phase of the quantum signal? Is there any offset? And if there is an offset, does that offset fluctuate because there are different frequencies? They are passing through the different, through the fiber, so they occur different phases. So does that phase change randomly? And in that case, how do you manage it?
Yes, so there is of course a phase offset, fixed phase offset, because your detector has maybe a different phase profile, but this is something that does not change. And I think the difference in frequency is rather low, right? It's just a couple of 10 megahertz. So we don't see any fluctuations in phase between the quantum signal and the pilot term, not randomly.
Okay, thank you. May one more thing. May I ask one question to Guang Shang? It's about the power limiting QKD, securing QKD system. But he completely forgot about the CV QKD side of it. At least some of the CV QKD attacks, they don't need much power. For example, the saturation attack. So in some cases, the power testing based on the power of the incoming signal doesn't work. It's a comment.
Oh, okay, thank you.
Okay, let's go on. Actually, Gong-Chan has also a question to Tobias.
Yes, I was thinking, is there any special reason for using like a 220 megahertz separation for the two lasers? Do you have to somehow lock it?
No, there's no particular reason in using 220 megahertz. Could also be less or more. You just have to make sure that all the mixing products do not overlap, so that they clearly are apart. And this is, yeah, what we ended up with. Yeah, there's no particular reason on that.
Okay.
Could be 400.
Can it be lower, like we set the wavelengths to be exactly the same?
Yeah, if it's exactly the same, then it doesn't work, because then you get into the homodyne detection regime. But we call that intradyne if it's close, because then you get mixing products between the different sidebands.
Okay.
In our case, this would not work. We would then need an optical hybrid to actually measure the other quadrature as well.
Okay. Yeah, another question is that, is it possible like for Eve to attack by also locking to, because you're sending a frequency reference, is it possible for them to lock to the frequency reference to do the attack?
Yeah, that goes back to the first question about the pilot tone. If the pilot tone can be attacked, I don't think so.
Okay, thank you.
Okay, well, I think we can go on for questions. But Christian, you agree on that? We don't have to close this session immediately. So we have a next question by Chao Wang, please.
Okay, thanks. Thank Wei Luo and Cao Ling for your great talk. So I have a question for you. So the first question is for the MDI chip-based MDI QKD, right? So I think some groups has demonstrated this kind of chip-based quantum transmitter, right? So they will observe some phase modulation related loss problem, right? So I'm wondering whether you also have this question, you also have this problem, and how you solve this problem.
Yeah, okay, thanks for the question. Actually, yeah, we have the similar problem with the modulation related loss, and it will influence the security of the system and open some loophole. So actually our solution, maybe we can solve this problem by adding an extra high-speed VOA, variable optical attenuator, to compensate the modulation related loss caused by the polarization in state encoder.
I see, but this kind of high-speed VOA hasn't been included in your current setup.
Yeah, in current setup, we didn't include in
I see.
this kind of VOA. Yes.
Okay.
But
okay.
Yeah.
Yeah.
In the next design, we will consider this problem.
Yeah. Thank you very much. And my next question, my second question is for Cao Ling. So because I noticed, right, the homodyne detector you are using it has a bandwidth of around maybe 10 megahertz. Because you only show the bandwidth of the homodyne detector to 10 megahertz, right? So, and you are also doing time multiplexing on the optical chip. So I'm wondering how long is your delay line on your chip? And how about the repetition rate of your system, right? Whether the long delay line on chip will introduce quite a lot optical loss to your system, right? Will it be a problem?
Okay. The operating rate of our system, the pulse repetition is about 5 megahertz, and we encode a signal by amplitude and modulator. The frequency is about 6 megahertz, and we use 20 meter off-chip fiber as the delay line. And the loss is the loss of the fiber is very small, but the coupling loss of chip is about 5 dB.
Okay. Yeah. Okay. Thank you very much.
Thank you. So maybe we come to our last question. Nitin, you can ask it directly.
Hi. So my question is for Chaolin. I hope I pronounce the name correctly. So you reported polarization extinction ratios of like 30 dB or even 40 dB, and as far as I know, typical fiber optical polarization beam splitters have like 20 dB, at the most 23 or 24 dB. So how did you get such a massive improvement?
Okay, thank you. We actually, on-chip or single PBS can achieve the extinction ratio about 25 dB. And we use two PBS together and the two cascaded PBS. And this can achieve much higher extinction ratio.
Okay, great. That explains it. Thank you.
Thank you.
Thank you very much. I pass the word to Felix for a conclusion.
Yeah, so thank you very much again to all the speakers for this great session. Now it's time to go to lunch, Q&A and networking in the meet and greet room. And then everything starts back at 12:45 with the tutorial by Maria Naya Plasencia. So thank you very much.
Bye-bye.
Gong, can
Everything works smoothly. Yeah, good. So you're organizing again QCrypt next year, right? So you're doing it this one with all the Zoom and everything, and let's hope next one it will be at Amsterdam, right?
The next one again, yeah, on-site one.
Yes.
We keep our fingers crossed, yeah.
I hope we'll be able to go to Amsterdam next year.
Hopefully, yes.
So the live stream is on.
Okay.
Fred, I guess you can.
Yeah.
We can start. Okay,
so welcome back, everyone. The next speaker is going to be Maria Naya Plasencia, who's a researcher at INRIA in Paris. So she will give a tutorial on new results on symmetric quantum cryptanalysis and perspectives. And just before we start, just a quick reminder on how to ask questions. If you have a question, you can either type it in the Q&A or raise your hand. And don't hesitate to ask during the tutorial or at the end, of course, there will also be a question period. So without further ado, Maria, you have the floor.
Thanks a lot, Fred. So it's a real honor for me to be here giving this tutorial today. I'm going to talk about a topic that was not so obviously interesting a few years ago, which is quantum symmetric cryptanalysis. So first, I will give quite a long introduction because I think it's important to explain the motivation, the context, and the state of the art of this topic. And then we will see an illustrative case on quantum cryptanalysis that will present some of the best classical and quantum attacks on two popular constructions, which are Even-Mansourian and FX, and also some recent new improved results that we proposed in QCrypt last year with a way of using offline Simon's algorithm. And finally, I will discuss some interesting open problems, and one more in particular that I've been personally very interested in it, but I haven't found a way to solve. So I'd be glad if someone has some ideas to advance in this direction. And we will end with a conclusion. So, well, that's quite a generic introduction. That you all know that the aim of cryptography is to enable secure communications even in the presence of malicious adversaries. There are two big families. One is asymmetric, that does not need to perform a key exchange prior to establishing the communication, but that is computationally costly, and has a security that is based on well-known hard mathematical problems, like, for instance, factorization. And the other branch, which is the one that we are going to be talking about today, is symmetric cryptography, that does need to perform a key exchange prior to establishing the secure communication, but that is very efficient. So symmetric primitives have an ideal security that is defined by the best generic attack. So for instance, if we have a block cipher with a secret key of size k, we can always recover this key by trying all the possible keys. So it would cost 2 to the k, and that's an attack that can always be applied, and that's what we call generic attacks. So in order to verify that the real security of the ciphers meets this ideal security, we need to perform continuous security evaluations, and that is done through cryptanalysis. And in practice, what happens in most of cases is we use a combination of both families in what are called hybrid systems. So the main important families in symmetric primitives are block ciphers, stream ciphers, and hash functions. And in this introduction, I'm going to use block ciphers to illustrate the main ideas I want to present.
Maria, just
yes?
sorry to interrupt you. We're
Sure.
having a bit of a slide sharing problem again, that we see only part of the screen.
Okay, yes. So you see.
Maybe in the worst case you can. No, not even worse.
No, that's worse. Okay.
Yes.
And
maybe you can shrink the. Yeah. Okay, now it works.
Okay, so I can try to adapt it like this. It's like optimal, I think, right? Okay.
Like this is good. Yes.
Okay, I won't move the shape anymore. Perfect. Thanks, Fred. Okay, so as I was saying, I will use block ciphers to illustrate this introduction. So in block ciphers, when we want to encrypt a message, this message is decomposed in blocks of a fixed size, and each block is transformed by the same function E of k. So we have a secret key k, and the plaintext goes through this encryption function to generate the ciphertext. And typically, E of k is composed of a round transform that is quite simple and that is repeated enough times so that E of k is robust. So the security provided by an ideal block cipher is defined by the best generic attack, as we previously said. So the best generic attack is an exhaustive search for the key, which goes 2 to the size of the key. And as we want that this is not doable by an attacker, typical sizes of the key must not allow the 2 to the k generic attack to be doable. So that's why typical sizes of keys are 128 or 256 bits. And what we want is that recovering the key from a secure cipher must need at least 2 to the k operations. We cannot do it in less computations. So how do we verify that the real security of the cipher meets this ideal security? And the only way of doing this, for now that we know in symmetric cryptography, is performing continuous security evaluations. And any attack that we will find that is better than the generic attack will be considered a break. And that's why we are often left with an empirical measure of the security that is done with cryptanalysis. It's important to understand the state of actual symmetric cryptography to discuss the competitions that have recently and a bit less recently taken place, which were competitions to find new standards or to cover new needs, like for instance, the AES SHA-3 or the currently ongoing lightweight NIST competition. And what this implies is that there have been many good proposals, many good candidates, or potentially good candidates. And there are 3 important questions, which are how to choose the ones that should be used, and how to be ahead of possible weaknesses, and to keep on trusting the ones that have been chosen. So the answer to all of these questions is with cryptanalysis. So when can we consider a primitive as secure? A primitive is secure as far as no attack on it is known. The more we analyze a primitive without finding any weaknesses, the more reliable it is. And that's why designing new attacks and improving existing ones is essential to keep on trusting the primitives or to stop using the insecure ones. So cryptanalysis is the foundation of the confidence in the primitives that we use. There is a very important notion that we are going to describe now, which is security margin. Because what happens if no attack is found on a given cipher? What can we say about its robustness? So the security of a cipher is not a one-bit information. So if we cannot attack a cipher, it's not yes, we can attack it or no, we can't. What we do in practice is to have a look at reduced round attacks. That means we said before that E of k is formed by the repetition of a usually simple round function. And so what we try to do is to see how many rounds we are able to attack, and this will give us the notion of the security margin of this primitive, which is how far is the primitive from being completely broken. Sometimes we also analyze the security of some of the components of the primitive, as for instance, in security proofs, we need to make some assumptions on these components. So we try to verify if these assumptions are verified or not, and if they are not, that means that maybe the meaning of the security proof is different. So it's very important then as a cryptanalyst to determine and adapt, keep on trying to find better attacks which will reduce the security margin. And this way we always want to know which is the highest number of rounds that can be reached by an attack. So just to say that we seem sometimes a bit too paranoid, but we think it's the way to go and to be able to trust the primitives we use. So sometimes we proposed attacks that have very large complexities. So for instance, as the keys that we use are large, we can find attacks that break a cipher with a very high complexity. For instance, 2 to the 120, which would be really far from practical for a key of 128 bits. But this is still dangerous because they imply weak properties that were not expected by the designers, and because experience shows us that attacks only get better, and that arrives very often, that a very high complexity attack actually with time finds improvements and has a complexity that gets reduced. And also because happily there exist many ciphers that do not experience these ugly properties. And also, so it makes sense that when determining the security margin, as we want to know really the highest number of rounds that we can attack, we push the attacks to the limit, which implies that sometimes the complexities we can reach are very high. But this allows us to compare primitives between each other and to anticipate problems. When the security margin gets very small, we might start to worry. So that's kind of the classical scenario. Let's see now what happens the post-quantum one, which is when adversaries will have access to quantum computers. So in the case of asymmetric cryptography, it's widely known that most widely used primitives would stop being secure, and that's why the community has been for a while now looking for replacements, as shows the current NIST ongoing competition. And the case in symmetric cryptography was a bit different, because for a long time it was believed that to counter, to resist, or to have an ideal equivalent security in a post-quantum world, it would be enough to double the key length, as Grover's algorithm allows to perform an exhaustive search in the square root of the classical time. But very little was known, and we have still a lot to learn about how to perform the cryptanalysis. We said before that it's so important when having quantum computing available. So also it's important to say that the existence of future quantum adversaries, it's already a problem for present existing long-term secrets, so we should start using quantum sacred primitives now. So there are two important tasks regarding symmetric cryptography: to conceive more cryptanalysis algorithms for correctly evaluating the security of these primitives, and use them to evaluate the existing primitives to identify new gaps of primitives that won't be secure anymore, and to design the ones that will be filling these gaps for a post-quantum world. Just a small remark on quantum attacks, because as we said before, an analysis is considered an attack when it's better than the best known generic attack, and quantumly the generic exhaustive search is accelerated. So that means that if we are not able to speed up an attack as much as the generic attack, a broken classical primitive might be unbroken in the quantum setting, which might seem a bit non-intuitive in the beginning. But this would just mean, for instance, that a primitive might not have 2 to the 56 bits of security against a classical adversary, but might have 128 bits of security against a quantum world. It's just because we will mention this later. So now I will present the main attacker scenarios that have been used in the literature, and and the related models. So mainly I could find 4 models that have been considered. We can define the model Q0, which would be just classical attacks with classical computers, so what we were doing until recently. Then we have the model Q1, which would include the model Q0, plus the adversaries have access to a quantum computer. Then we have the model Q2 that would include the model Q1, plus the access to superposition queries to a quantum cryptographic oracle, while in Q1, all the queries are classical. And then we have the model Q3, where we consider Q1 plus superposition queries to the differences of a secret key in a quantum cryptographic oracle. I will say a bit more about these models right now. So, well, Q0, there's not much to say. It's just the classical attacks with classical computers. And regarding the model Q1, which is quite a meaningful model because it just supposes that the adversary has access to a quantum computer. So far, the best we have obtained is quadratic speedup, but sometimes the speedup is smaller. That means that if we are considering exhaustive search attacks, if a primitive is safe in Q0, it will also be safe in Q1. So does this mean that so far these exhaustive search attacks in Q1 are not interesting? No. So for me, that's not the case at all, because some people might think that's okay. So if it's safe in Q0, what's the point in looking at it in Q1? So my opinion is that in a post-quantum future, classical or quantum surnames will disappear, and the expected security will be given by the best generic attacks, for instance, Grover. And we will still need to define a security margin to see how far is a primitive from being broken. And this will be determined by the highest number of rounds cryptanalyzed with any attack, classical or quantum. And that's why these kind of Q1 results regarding exhaustive search attacks are important information needed for determining the unique and feature security margin. There's also important thing to say. So in Q1, which is a very recent result from this year QCrypt by Akinori Yasuyama and Yu Sasaki. And that is regarding collisions, we don't have the same scenario as exhaustive search, as the quantum collision speedup is less than quadratic. So Akinori and Yu managed to show that we could build quantum rebound attacks, so collision, a type of attack to find collisions on hash functions that could reach more rounds quantumly than classical attacks, which was a very interesting result. And then we will see what can we say about the model Q2. So it's a very powerful model because I recall that the adversary is able to perform superposition queries to a quantum encryption oracle. But I believe, yes?
We have a question from
yes.
Jules Brassard. Who
Yes.
wants to know, in the Q1 model, how could you apply Grover's algorithm if you're not allowed to ask queries in superposition?
So, for instance, yes, thanks. It's a very good question. So we can apply it, for instance. So in this example I gave, it's because there are hash functions. So as there is no key, there is no superposition queries to be performed, and so that's one thing. That's how you can use Grover. And the other one is that sorry. When you apply Grover, it's the generic attack, and you don't need to perform queries to a quantum encryption oracle. You just know. So the block cipher description is public, and there's a secret key, but you can implement the description of the block cipher, and you can try all the keys. And this, you don't need a random oracle for doing it. So the generic attack can be done. You can do it on your quantum computer without needing to perform any superposition queries. Okay?
Yeah.
You just try. That answers the question?
It does to me. Yeah.
Okay. Okay.
I appreciate that. So thank you.
Okay, perfect. Okay, so now we arrive at Q2. And we were saying that it's a very powerful model. But I believe that there are many good reasons to study security in this scenario. So I think the first reason is that it's a very simple model, and that's why it is used in many security proofs. So it seems It's a quite controversial model because some people think it's, well, at least in our community, that the results are super scary and that it's very important. And some people think that that attacks in the Q2 model are not important at all and that no one cares. And I will, in the final conclusion, I will talk about this a little bit more. But here I will just give some reasons why I think it's a model worth studying. So one is that as I said, that it's simple, that it's used in many security proofs, and I think it makes no sense defining a model for security proofs if we are not allowed to try to attack the primitives also in that model. Also, it's a non-trivial model, and by this I mean that many constructions still seem resistant. And also, very importantly, I think, is that it's inclusive of all possible intermediate scenarios, like when the primitives will be used in larger protocols that might for instance, have obfuscation, or when they are implemented in hybrid machines that will have some quantum modules. And I think it's also important to say that, well, some people said that we could just counter Q2 attacks by performing a measure at the input of the primitive. But I think it's very hard to say that this will be able to be done efficiently, in particular when, for instance, we cannot trust users to do some much more easier tasks, like, for instance, stopping or respecting the maximal number of blocks that can be encrypted with the same key. So I think that there are a lot of scenarios where this is not that clear. So I think it's worth studying at least. So it has been defined and used in many results, proof-related and attack-related. And so I think that it's safe to say, and everyone would agree, that at least if we find an attack in Q2, we need to be extra careful when implementing the primitive in a quantum computer and using it in certain applications. But we will come back to this later. And so the third model was Q3, that I recall was the model Q1, with, in addition, superposition queries to the difference of a secret key in a random encryption oracle. So Reuteler and Steinwand in 2015 showed in a very nice result that this model is so strong that everything is broken. So that means that this is a too strong model, and it's not very interesting to study it because it's trivial. So everything would be broken here. There is another possible scenario classification of attacks, depending on if we are allowed to use big amounts of quantum memory, or if the quantum memory is limited to a polynomial amount. So we will call it scenario A and B. So I think that both are interesting. Of course, as before, attacks in less powerful scenarios are more meaningful. But as we said also before, it's not a one-bit information. If we don't find attacks in less powerful scenarios, it's also interesting to have information in some other scenarios. I think also results in scenario A are interesting from a theoretical point of view and also allow to consider previously unknown trade-offs. And while the second one is a more realistic scenario. So let's see now a little bit the evolution of the results in quantum symmetry cryptanalysis. The first result appeared in 2010. So Gaëtan Laurent proposed a quantum analysis of the QVASH candidate of the SHA-3 competition. And Kuakadan Mori proposed an attack using Simon's algorithm on a 3-round facetel. Also, Kuakadan Mori in 2012 proposed also to use Simon algorithm to attack the even-Mansur construction that we will see later. And Mark Kaplan in 2014 proposed a quantum meet in the middle attack on iterated ciphers. And in 2015, Reuteler and Steinwand published the results on quantum-related keys that we mentioned before. So I think these results were not published in well-known conferences, and that's a pity, I think, because at least in my community, these weren't very well-known results, although they are very interesting. So more recently, in around 2015-16, with Mark Kaplan, Gaëtan Laurent, and Denis Leverrier, we proposed new results using Simon's algorithm inspired on Kuakadan Mori's attacks, but on new modes and new constructions, and also to speed up slide attacks, which implied the first speed up of classical cryptanalysis better than quadratic. And also Santoli and Schaffner published similar results 2017 independently. And in 2016, we proposed also quantum attacks on differential and linear, so a quantized version of differential and linear attacks. I forgot to say, sorry, before that I was trying to respect a little bit the colors of the models that I mentioned before. So the things that will be in pink are the attacks on Q2. The ones that are in kind of green olive are Q1, and the orange one was Q3 that we won't be seeing much more. And the ones in blue are kind of generic algorithms that can be applied depending on the applications in Q1 or Q2. So I'm sorry for colorblind people. I hope it can still be distinguished a little bit. So after the results from 2015 and 2016, I was very happy to see that a lot of different cryptographic groups and colleagues started working on the topic. So there have been many interesting results that have appeared on this. And in our team, we are very lucky to have an ERC for working explicitly on this, which allows us to expend a lot of time and a lot of manpower. So we have reached, this is a non-extensive list of results we have reached in the last years. And this is possible thanks to my two very bright students, Xavier Bontin and Andrés Rothenloher, and Antonio that recently arrived, as well as the colleagues from my team, in particular, André Chailloux and Anthony Leverrier, which are quantum experts, and also the colleagues from NTT, Yu Sasaki and Akinori Osoyamada. So I don't have the time to talk about everything. We will see in the next section offline Simon attacks that were presented at QCrypt last year. And yeah, that's for it. So I will now discuss a little bit some useful, so the quantum tools that I've found in the literature that have been useful for providing improved attacks. And so I won't go into the details because I'm sure you all know much better than me all of these algorithms, but I will just try mainly to present the problems that they solved and how do they appear in symmetric cryptography, and what is the main speedup regarding classical algorithms. So one of the most used algorithms is amplitude amplification that solves the exhaustive search problem that we already talked about. That is, given a function, a Boolean function of n bits to 1 bit, find one element x such that f of x is equal 1. So classically, the complexity is about 2 to the n divided by the number of elements such that f of x is equal 1, so the support of f. And quantumly, the number of iterations, it's the square root of the classical complexity. So it has many applications in symmetric cryptography, not only, for instance, in key recovery, but it appears a lot when we are applying dedicated cryptanalysis. Sometimes it's very useful for speeding up some steps of the attacks that we are trying to solve. Another algorithm that is also useful is quantum counting, and this one solves the problem of distinguishing a bias distribution that is given a Bernoulli distribution determined with high probability whether it is biased or not. So classically, we need about 2 to the 2 epsilon. So 2 to the minus epsilon is the bias. So we need the 2 to the 2 epsilon data in order to detect this bias. And quantumly, thanks to the algorithm from Brassard, Oyer, and Tapp, it's the square root. And this algorithm is very useful for linear attacks. And we will mention it later when we will go back to linear attacks for the open problem I wanted to detail. So another algorithm that has been widely used is the quantum collision search algorithms that solve the collision problem that is given a random function h on n bits, find two distinct elements such that their image through h is the same. And classically, it can be solved with the polar Ross algorithm in 2 to the n over 2. And quantumly, in scenario A, that is with big quantum memory, it can be solved thanks to Brassard-Oyeran-Tab with an optimal time complexity of 2 to the n/3, optimal query and time complexity, while needing the same amount of quantum memory. And there are also some other algorithms for solving it in scenario B. Another popular algorithm in symmetric quantum cryptanalysis is Simon's algorithm, which solves Simon's problem, that is given a Boolean function f on bits, and the promise that there exists S such that if the image of 2 distinct elements through f is the same, the XOR of both elements is S, we want to find the S. So for solving this classically, we can do it by trying to find a collision, which would give us S. And this is with a cost of 2 to the n/2. And quantumly can be solved with Simon's algorithm in a much better time complexity of O of n to the power of 3, and the number of queries is O of n. So this might seem like quite an artificial problem, but actually it's very easy to recognize it in several situations in symmetric cryptography. We will also see later, for instance, Even-Mansour and the FX constructions where it can be applied. And another algorithm that is related to the previous one is, well, the problem is related to the previous one, is Kuperberg's algorithm that solved the hidden shift problem with modular addition. So Simon solved the hidden shift problem with XOR. And here we have F and G that are 2 injective functions. And we have the promise that there exists S such that f of x it's equal to g of x plus S for all x. We want to find S. So classically, it has the same complexity as before, as it comes down to finding a collision. And quantumly, it can be solved with Kuperberg's algorithm in 2 to the O, about 2 to the square root of n. So these are the main tools that have been used for now. I think, and I hope some new tools will prove to be useful in the future. And I will just list now some of the tools, dedicated tools for symmetric cryptanalysis that have been proposed. So there are some new quantum collisions algorithms in scenario B proposed that have worse time complexity but do not need a QRAM or a large amount of quantum memory to be performed. Also, we propose some quantum cakes or algorithms that improve the previous known complexities, or Sasaki and Oseyamada propose some multi-collision algorithms that were very interesting. We will see the Grover meets Simon one for attacking the fixed construction that was proposed by Leander and May in 2017, and also the offline Simon algorithm that we proposed last year. So the ones in blue are the ones that I will talk about later. And there's also a Simon meets Kuperberg where we solve the problem of the hidden shift when having several parallel modular additions, which is also a case that happens often in symmetric cryptography. And then we also have some more dedicated tools. So now we have finished with the introduction, and we are going to talk about the illustrative quantum cryptanalysis case that I mentioned before. So first, we will describe the Even-Mansour construction. We will present some of the best classical attacks on this construction, and next, the best quantum attacks in Q1 and Q2 that were previously known. Next, we will describe the FX construction and the Grover meets Simon attack in Q2 by Leander and May. And next, we will present the ideas for reducing the number of queries of this FX attack. And finally, how to apply the offline Simon in the previous construction. So Even-Mansour proposed in '97. It's a construction that from a public random permutation builds a block cipher. So we have a permutation P on n bits and two n bits of key K1 and K2. And if we want to encrypt a message X, we have to XOR first the key K1 to it. Then we apply the public permutation, and then we XOR the second key K2, generating this way the ciphertext. the size of the plaintext and of the ciphertext is n, as well as the sizes of both keys here. So we know that any classical attack requires that its time complexity times its data complexity will be at least 2 to the n. And data complexity are the queries to an encryption oracle, or the number of plaintext that we can ask to receive encrypted with the secret function to perform the attack. So, for instance, one of the attacks that verifies this t times the constraint is we could, with 2 pairs of data, guess K1. So once we have guessed K1, with 1 pair of data, we will have determined K2. And with the second pair of data, we can verify if those values for K1 and K2 verify that P2 encrypts to C2. So that means that with only 2 pairs of data, we can try all the values of K1 into 2 to the n, and this will allow us to recover both keys. We could also perform a collision attack, a collision search on the function f, that will allow us a different trade-off of data and time. So if we define f of x like the encryption of a value x XOR p applied to x, we can see that f of x is equal to f of x XOR k1, as the encryption of x is equal to k2 times p of x XOR k1. And this would give us the same value for x and for x XOR k1. And in this case, we just want to find a collision between 2 different inputs to f, and this will allow us to retrieve the value of k1. And this would give us a complexity of time and data of 2 to the n over 2. But here, all the calls to f implies queries to the encryption function. That means that the data with this attack would not be smaller than 2 to the n over 2. So in 97, Diamond proposed an attack that allowed to have improved trade-offs with smaller data. For this, he defined 2 functions, h of x and g of x. H of x was equal to the encryption of x XOR the encryption of x XOR 1. So it's a differential attack because we see that there's a difference between the 2 inputs. And g of x was equal to p of x XOR p of x XOR 1. So it's important to see that g of x does not imply queries to an encryption function because the permutation p is public. And with h and g, we see that g of x XOR k1 is always equal to h of x. So that means that we can perform kind of the same collision attack as before, but now the queries to G won't be queries to the encryption oracle, and we have a trade-off. We have a better, wider curve of trade-off where.
Yeah, quick
yes?
question from
Sure.
Jill again. What is D?
So yes, so D is the So I forgot to say it before. I'm sorry. So D is the data complexity. Yeah, no, I said it, but in the slide here, I think this is data complexity. That means the number of queries we perform to the encryption oracle. That is how many plaintext we give, so that we get back the ciphertext encrypted with the secret key. Okay, that's fine.
I think so.
Okay. If there are more questions on, yeah, don't hesitate to tell me. It's the data complexity. It's the number of pairs that we query. So, for instance, in this attack where we have G equal 2, that means we have P1 C1 and P2 C2, verifying that P1 encrypted with the secret key is C1 and P2 encrypted with the secret key is C2. Okay, so it's the number of pairs plaintext ciphertext encrypted that we recover. So yes, we have seen that with Diamond's attack, we have many more trade-offs where we can reduce the data complexity. So what can we say quantumly about Ibn Mansour? We mentioned before Kouakad and Mori and their 2012 paper. And in this paper, they also proposed Q1 attacks with big quantum memory. So it's easy to see that in this attack where we are looking for a collision between H and D, we could apply, for instance, the DHT algorithm that would allow us to find a collision with a complexity of D times t to the power of 2 equal to 2 to the n, with a need of d QRAM. So we could, for instance, we could query, for instance, h of x 2 to the n over 3 times that we will store in a QRAM memory of the same size. So d equal to the n over 3, which are the queries that we have applied. And next, with G, we will perform an exhaustive search to find a collision with the stored list. So it would cost us 2 to the n over 3 time also. In 2018, so Yamada and Sasaki proposed to use an algorithm we presented in 17 for solving the collision problem where no QRAM was needed, but you need a classical memory of 2 to the n over 7. So they could also attack even Mansour in Q1b with a data and time complexities of 2 to the 3n over 7. And Kuwakada and Mori also proposed an attack in Q2. And it's quite easy to see that we can directly use Simon on f. So f is a function I wrote down before in the beginning, which is the encryption of x XOR p of x. So this function has a period k1 because, as we saw before, f of x is equal to f of x XOR k1, and this is exactly Simon's problem. So if we are allowed to perform superposition queries on x, we can apply Simon here, recovering k1 in polynomial time. So this is previous results on Ibn Mansour, and it leaves some open questions. One obvious one is, can we improve these previous quantum attacks, or are they optimal? And another one is, can we use Simon's algorithm in Q1, which we didn't know how to do before. So before answering these questions, let's go have a look at the FX construction, because what we're going to do there is going to be related. I think it's easier to start by talking about the FX construction. So the FX construction is it's very interesting when talking about post-quantum symmetry cryptography, because it's a natural extension for doubling the key length for countering Grover's attack. So it's similar to the Ibn Mansour one, but instead of having a public permutation P, it has an encryption function E of K with another secret key K. For the sake of simplicity here, we will consider that the secret key K, it also has a size N as K1 and K2. So classically, the best attacks on the FX construction verify that the time complexity times the data complexity is at least 2 to the 2n. So classically, we see that the bits of security are doubled here. And in 2017, Leander and May proposed the Grover meets Simon attack, where it was an attack on Q2. And the idea was to search with Grover the secret key K of the middle encryption function. And so they will apply Grover in a variable K prime, and they will use Simon's attack on Ibn Mansour as a test in each Grover iteration to check if the corresponding function fk prime has a period. And fk prime is like the f we had before, but instead of XORing to the encryption p, we are XORing e of k prime, which is the function we have in the middle, and for a particular value of k prime, it will be known. So we can apply Simon to fk prime, which would tell us if there's a period or not, and for the correct guess of the key, there will be a period. So the time complexity of this attack will be n to the power of 3, which is given by the test of Simon, times 2 to the n over 2, which is the cost of the Grover search over k. And the data complexity will be n times 2 to the n over 2, which is the number of times we need to perform n superposition queries for performing the Simon attack on the test. So what we try to do first is to reduce this data complexity. And so the main idea is, if we have a look at fk prime, which this is a joint work with Xavier Bontin, Akinori Yamada, sorry, the P is me also, and Andres Rotenloer and Yu Sasaki, that appeared at AsiaCrypt 2019. So if we have a closer look at Fk prime, we see that the first blue term, Fx of K1, K2 of X, depends on the encryption oracle, because it's there are directly calls to the encryption oracle, but it does not depend on K prime, on the value that we are guessing. And also we can see that the second term, the red one, depends on the guess of K prime, but does not depend at all on the encryption oracle. So the intuition of the idea for improving the number of queries here is that in order to reduce the data complexity, it would make sense to make only one superposition query or a few superposition queries to the encryption functions and reuse them, if possible, in each test of the Grover computation, in the Grover iterations. So more in detail, what we do is pre-compute O of n states that will each one contain a superposition query to the encryption function. And next we apply Grover, and in each Grover iteration, we perform a test that will compute the superposition of AK prime of X on the pre-computed states. Next, we'll check with Simon if this is periodic. And next, we will undo the computation in order to get back to the original superposition states of X, K, K1, K2 of X, in order to be able to reuse the states in the next test of Grover. So with this procedure, we are able to reduce the data complexity to O of n, instead of the 2 to the n over 2 that Leander and May had in their attack, while the time complexity stays the same. So now we go back to the question of, is it possible to apply Simon in the Q1 setting? So one natural idea is to, instead of performing superposition queries, to try to simulate them. So we could, for instance, perform, if we want to simulate one superposition query to the even answer construction that we have here, we can perform 2 to the n classical queries for all the values of X, and then we build the superposition state. So this would allow us to simulate one superposition query, but it would need 2 to the n data and time, which is not very interesting because this wouldn't be an attack. So what we proposed was separate the key K1, for instance, in 2 parts. And the intuition is that one part of the key K1 will be used in a Grover search, and the other one will be used in as a hidden shift and will be involved in Simon's algorithm. So if we separate, for instance, the inputs in a part with u bits that will receive as input X, and a part with n minus u bits that will have a fixed input of 0, and the keys, the key 1 is separated into parts also, key 1, 2, and key 1, 1. So the blue one here in the down part and the black in the upper part. We can rewrite actually this construction the following way. That, as you can all see, it looks a lot like the FX construction that we mentioned before. So we have, sorry. So here we have an input on u bits, which is smaller than before, for it's like key K1. And we can imagine, or we can consider that the other part of the input that will have a fixed plain text part 0 is directly the key K12, which will be a parameter of the permutation P. And next we have K2, and we generate the ciphertext. So here we could, if we can perform exactly the same attack as was done in FX, by guessing the n minus u bits of K1, 2 with Grover, and the remaining u bits here will be, the remaining u bits of K1, 1 will be the secret period of Simon. So all we need to do now is to generate the superposition of all these X, which can be done in 2 to the u now, which is smaller than 2 to the n. So applying the attack with these ideas, we will have a data complexity of 2 to the u classical queries, which are the ones we need, about 2 to the u classical queries, which are the ones that we need for building the superposition one, and a time complexity of 2 to the u for building the simulating the superposition query, plus 2 to the n minus u divided by 2, which is the cost of building a grover over k12. So this implies a trade-off curve of d times t squared equal to 2 to the n. So if we compare the results using these ideas to the ones we had before, which are the ones with the references in red here, we can see that we can improve in even Mansour, we can improve the previously Q1 known attacks. So we can be in Q1B while before it was Q1A. So here, the attack in Kuakadwa Mori of 2012 needed a quantum memory of 2 to the n over 3, while now we only need a polynomial amount of quantum bits. And when we compare to the other Q1 attack that we had before, our query and time complexity is much improved. And in the case of X2, we can considerably improve the amount of queries that we need to perform the Q2 attack. And in Q1, we improve both the queries and the time complexities. So to conclude this part, we have proposed the best known attacks on Q1, Q2 for Ibn Mansour and FX, which can improve memory, queries, or time depending on the case. And also we have proposed the first Q1 attack that uses Simon's algorithm. Also, there are other applications of these ideas, like some kind of slice attack, or the related key attacks in Q1 also can benefit from this speed up. So that's for the illustrative case. If there are no questions for now, I will go to the open problems, and I will list some of the open problems that I consider very interesting right now, and then we will go a little bit into detail to see how to improve the key search of linear attacks quantumly. So as I said, there are many things to do still. I think an important question is to propose an efficient authenticated encryption mode that would be QCsafe. And by efficient, I mean in one pass, like OCB, for instance. Also, could we find a new out-of-the-box quantum attacks using new tools like the QFT, for instance? So I think there are a lot of things to try. Also, it would be very interesting to study the quantum security of the lightweight primitives that are now being in consideration of the NIST competition. Is there a generic way to provide key length extensions on the primitives in order to resist to the best generic attacks quantumly? I think also one of the a point that hasn't really been taken into account until now is, okay, we say we need the bigger keys for having an equivalent ideal security in a post-quantum world, but we haven't thought a lot about what happens with the state. So if the state, which is of course harder to increase, and that's I think why we don't often talk about this, if the state stays the same, I think this might be a problem if we want to have a very high security regarding the key search. This would imply some problems, some attacks in the modes when we try to collide in the states. So I think having functions with bigger internal states would also help avoid this kind of problems quantumly. And also in Mark Stevens' FSC talk in Brussels, he talked about trying to find improved quantum attacks on hash functions. He talked about SHA-1, I think. So I think it would be very interesting. Also, there's a lot to do regarding hash functions, as Yu Sasaki and Akinori Yamada showed us in QCrypt this year. And I think it's a field that needs a lot of study yet. And also, it would be very important to look in detail about evaluating possible quantum implementations of algorithms. And then, of course, proposing quantum versions of integral saturation in possible boomerang attacks. All of this. But now I'd like to talk about something that I've been trying to do for quite a while, and that I'm a bit obsessed with, maybe. So that's why I wanted to share it with you. Yes.
Maybe before going in there, there's a question from
Yes, sure.
Sharma. Is there any quantum attack based on entanglement properties rather than superposition quantum state attacks? And
No, not that I know of. Sorry?
And if so, how can we deal with such types of attacks?
Okay, no, I don't know about it, and it would be very interesting if he has some ideas, I would be really interested to discuss it. Thanks.
Thanks.
Thank you. Okay, so if there are no more questions, I will then go back to the next part, which is a part that if it wasn't for the pandemic, I think I would have done on a blackboard. So I tried to simulate the experience doing the slides by hand, but I'm not sure if I'm fully satisfied with the outcome. But well, here we come. So we will talk now about the linear cryptanalysis that was proposed at Matsui in in 96. And I will try to explain here a simplified version of linear attacks in order to provide the intuition of the problem I think would be very nice to solve. And also, when talking quantumly, we will talk mainly in Q2 because it would already be super nice to improve the known complexities in Q2. So the most basic version of attack that Matsui proposed in 96 was the linear distinguisher. So that is given if we have a block cipher E of k, if we can find an affine approximation involving some bits of the plaintext that are given by a linear mask alpha and some bits of the ciphertext that are given by a linear mask beta, such that this affine approximation has a bias 2 to the minus epsilon, we could distinguish this construction from a random permutation by recovering 2 to the 2 epsilon pairs PC, and then we will be able to detect the bias. So that's the principle of the linear distinguisher that Matsui proposed. And quantumly, as we saw in 2016, this complexity can be improved using the quantum counting algorithm. So instead of 2 to the 2 epsilon pairs, we would need 2 to the epsilon pairs. So the next step of the attack, Matsui's algorithm 2, was to perform a last round key recovery attack using a linear approximation on R rounds that will attack R plus 1 rounds. So in this case, the affine approximation that we have, it's between P and C prime, which is a partial internal state instead of C, which is the ciphertext. And from a certain ciphertext C, we will need some bits of C and a value, a part of the last secret key K out in order to compute C prime. So if we want to compute in the affine approximation beta times C prime, we will need a certain amount of bits of C, which is, and a certain amount of bits of the last round secret key. And this amount of bits is the same because they are stored in the last step. So we will call it size of K out, the number of secret bits that we'll need to guess in order to compute C prime, in order to compute beta times C prime, and this is the same size of the involved bits of the ciphertext. So how would the attack work in this case? Well, we can just guess the bits we need from the key to compute C prime, or the needed values of C prime, and for each value, we will check if when computing the affine approximation for all the pairs of data that we have, we detect a bias or not. So we suppose that we will only detect a bias when we are guessing the correct value of K out. So that means that the time complexity in this case is going to be 2 to the K out for each guess of the bits we need in order to invert this part for being able to compute beta C prime in the affine approximation, times 2 to the 2 epsilon, which is all the data we need to detect the bias. But we are going to see next that this can be improved. So up to now, we could propose a quantum version of this attack, which was as before. The data one, we can use the quantum counting algorithm and it will be the square root. And the time complexity will also be the square root, as the search of the key out bits can be done with Grover, and the data also, the data we need to try for detecting the bias is also reduced with the quantum counting algorithm. So quantumly, we have a square root complexity when we are in Q2. And now it comes the part where I haven't been able to say something interesting for now quantumly. So we can improve the last round attack from Matsui if 2 to the 2 epsilon is bigger than 2 to the k out. So if the amount of data that we need is bigger than all the possibilities for the bits of the secret key that are involved, we can improve this algorithm by using distillation. And the complexity is going to become 2 to the 2 epsilon plus 2 to the 2 k out. So let's see how we arrive to this complexity. As we said, the amount of data, 2 to the 2 epsilon, is bigger than 2 to the size of the last of the bits involved in the inversion we need to perform in the end, which is the same size as the bits of the ciphertext that are needed to perform this inversion. So we can build a table T of size 2 to the size of k out, from 0 to 2 to the size of k out minus 1, where in each, at position I, we will store the number of times alpha p is equal to 0 for all the pairs PC from the data that have the value I in the size of k out relevant positions of C. So that means that we take all the pairs of data PC that we have, and we will make groups for the ones that have the same values in the relevant bits of the ciphertext. So these relevant bits of the ciphertext can have values from 0 to 2 to the size of k out minus 1, and each time we will compute the number of times all the p's associated to those ciphertexts verify alpha times p is equal to 0. So the cost of doing this is going to be 2 to the 2 epsilon, because we have to go through all the data that we had stored. So once we have built this table T of size 2 to the size of k out, we can now, for each guess of the value of the secret key k out, go through all the table and compute the associated correlation. So the cost of this is going to be 2 to the 2 size of k out, because we have to guess k out, which is 2 to the k out, the size of k out, times going through the table, which is also the same size. So this can be done in 2 to the 2 size of k out, which with these two terms in green and blue, we see we recover the complexity that I said before, which is better than the one we had with the naive approach. But this complexity, the blue one, can still be improved. So for improving this, this was proposed by Collard, Standard, and QCrypt in 2007. We will build a slightly different table T of I, where in position I, we will store the sum over all the ciphertexts that have the value I in the relevant positions of -1 to the alpha points p, alpha times p, sorry. Okay, so we compute here not the number of times alpha times p is zeroed as we did before, but we compute the sum over all the ciphertexts that have I that corresponds to the relevant bits of -1 to alpha times p. And next we will build another table, L of j, that will correspond to the values of -1 to the beta times c prime when k out equals 0. So here at position j, for instance, we will put the value -1 raised to beta times c prime when c, so for a ciphertext such that the relevant values are j, and here we store the associated value that will affect the affine approximation. And this table would be the one that corresponds to this value here when k out is equal to 0. But we don't know what is the value of k out. So what we actually want to compute with these two values is the sum that we can see here in the pink square. So we want to find the k out that maximizes the absolute value of this sum, which is the sum over all j of t of j times L of j XOR k out. Because we want to find the shift between the two tables that when we multiply the values, we will find the biggest value in total, because this would give us the highest correlation. And this can be efficiently done with the fast Fourier transform with a cost of size of k out times 2 to the size of k out, instead of 2 to the 2 k out. So this is the best complexity we have for key recovery linear attacks. So with the last improvement, we have a data complexity that is still 2 to the 2 epsilon, and a time complexity that is 2 to the 2 epsilon plus size of k out times 2 to the size of k out. And so my question here, is there a way of efficiently speeding up this improved attack using quantum tools, such that it's interesting regarding the other quantum attacks? Because so maybe methods too close to the classical one don't seem to work better, because for instance, for using distillation, we would already have to go through all the data, which would already cost more than we are allowed to. So yeah, we've been thinking about it for a while, and for now, if someone has some ideas, I will be very happy. And so we will now reach the final conclusion. I don't know, Fred, if there are any questions in the meanwhile.
Not so far, no.
Okay. So yes, so I think the general conclusion is that there's no reason to panic, because symmetric crypto seems to be holding on well. For me, I think the most important outcome is that we should consider a bigger internal state in the primitive. There's something that I haven't mentioned, but it's quite nice that several times it has happened that some ideas that we've had for proposing quantum cryptanalysis have improved also, have been useful for improving the classical analysis we knew, which was also a bit surprising. But it happened, for instance, when improving quantizing the Mercy-Selzuk meeting the middle attacks on AES, that we, in order to make the quantum attack work, we had to propose a way of solving things that was not intuitive at all classically. And actually, if you do it also classically, you can reduce the memory needs. So it was quite nice and surprising. And I think there are a lot of things yet to do to precisely evaluate the security, to find the best attacks, to adjust the parameters. There's a lot of work to do. And just a short word about Q2, because I mentioned it before. So as I said, there's no consensus about the importance of results in this setting for now. So some people say surprising scary results, and some people say useless mode. So in my humble opinion, I agree it's a very strong model, but when possible, it would be better to avoid Q2 attacks. So we have, I have tried to show that in symmetric cryptanalysis, we are, well, our way of working works quite well, and I think it's because we are really paranoid. So attacks on 2 to the 200 declare sometimes ciphers broken. So I mean, I think we are never too safe, but that's just my opinion. So I think that at least it's information worth knowing. So just to conclude, I want to say that there are lots of things to do. Also, a lot of things to do in asymmetric cryptanalysis, of course. I think there's a real necessity to evaluate more the concrete security of the proposed primitives of the NIST competition, and there are possibly links between algorithms that work for both types of primitives. So just, yeah, so if someone is interested in working in these topics or in the open problem or whatever, please don't hesitate to contact us. Thanks.
Well, thank you, Maria, for a very nice tutorial. I'll just applause here on behalf of the audience.
Thanks.
So we have time for questions. Please don't hesitate to ask questions. And we already have one from Chris. Go ahead.
Yes, I have a question. Like, so most of the speed ups that the quantum cryptanalysis gives over classical cryptanalysis are of polynomial nature. So how do you kind of answer the concern of people who study the actual implementations of, say, Grover search, and then the square roots basically go away if you start counting gates?
Yes. So, sorry. So the question is, how do you?
Well, how do you deal with this concern that some people are saying, well, if you actually look at, I mean, there have been the studies now, like trying to break AES keys with Grover search, but if you look at the gate counts, then those are sometimes worse than even just classical brute force attack. So then they say, oh, we don't worry about Grover polynomial speed ups. This is not going to happen.
So, and you don't think implementations can get better, or I mean, gate counts can?
Well, I don't know. I'm sure you have been asked this question before, no? Like
yes. So yeah, I think that's why in the open problems, I think it's very important also to look at gate counts and all of this. But I think that from a theoretical point of view, it's also very important to not only rely on the implementation. Would be to so we don't know exactly how much things will cost. I mean, in the future, and I think it's better to be prepared anyway. And I think there are two parallel directions that are very important to work on. But I think it's just saying, okay, well, this game counting nearly catches up with the speed up means that we will stop caring about it. It's not the way to go. That's
okay.
One.
And yeah, maybe I have a question as well. So in recent years, there's been a lot of research trying to pin down various quantum versions of security definitions, like quantum versions of CPA, CCA, etc. And maybe you could comment a bit on the difference between, like, how do those definitions connect with the Q1, Q2 model, etc.
So I think it's very hard to connect. So I'm not expert in security proof at all. So I get lost easily with all of these notions. So I'm sure Christian could comment better on this than me. But so I think it's a bit super complicated, and we've been trying to work on the Q2 secure authenticated encryption mode that works in one pass. So we have something that should work now, and it's true that there are a lot of problems with the definition. So yes, I think there are still a lot of work to do in that direction too. I don't know, Christian, what do you think, or what would you say about this? But
I agree. I mean, the stronger you make these models, the Q2, I mean, basically, I think stuff that is secure in Q2, it will also be able to handle quantum data.
Right. So I guess the like Q1 would be some sort of version of CPA security, right? So I guess it'd be interesting to, and I guess Q2 is not really CCA or anything like this, right? So I guess it'd be interesting to see what happens in a CCA model. Like, can you get stronger attacks or something like this?
Yes. Sure. Yes, would be nice.
I do have another question. Like, you were showing these quantum attacks on the FX mode, but somehow, how do they compare to the classical attacks in the end? Like the best ones you find classically. What is kind of the time memory trade-off if you multiply these things, if you compare it to classical?
So in the FX attack of Leander and May, which was very nice, I think, when you multiplied that on time, you still had 2 to the n, which is kind of what you want to have quantumly, right? Because FX construction classically gives you 2 to the 2n. So you say, okay, then when Grover, you are comparing with the square root. So if you have d times t 2 to the n, which is what Leander and May gave, should still be fine. But the thing is that with the query improvement that we proposed, this multiplication goes down. So then you have d times t, it's 2 to the n over 2, kind of. So it's much worse security-wise, I think.
So that's an indication that this FX is not just gonna like double the security for you.
Yes, that's it. Yeah. So it was kind of a surprise in the paper of Leander and May in 2017, because the time could go to O of n over 2 times to n over 2. But with additionally, with the improvement in the queries one, even the product does not respect the equivalent notion that should maybe be considered quantumly. So yeah.
Do you have lower bounds for this? So do you know how
So actually working on the authenticated encryption one, we kind of found that for even Mansour, the Q1 attack that we propose is kind of optimal. But it's also very recent, and I think there is still a lot to do to prove which ones are, more bounds, and it's still new, I think. But yeah.
I have a quick technical question, Maria.
Yeah.
So this quantum algorithm that you mentioned for distinguishing a biased from a non-biased distribution, how does this quantum algorithm have access to the distribution? Does it get sort of a superposition where the probabilities are then the amplitudes, or?
So I think it's kind of a variant of the amplification amplitude one, right? You need a superposition in the inputs, in all the inputs. It only works in Q2 anyway.
Sure. But right, for distribution, you don't have an input. I mean, that's sort of why I'm asking. Right, classically, I guess sort of a classical distinguisher gets sort of samples which are independently chosen from this distribution.
So I think you just build a superposition. So you get all the you have all the inputs, right? You get superposition on all the X and all the that will generate all the outputs, and then there you are able to verify. No, sorry, maybe I don't.
Right, sort of a classical distinguisher for one distribution from another, right? He has access to samples from, well, one or the other distribution, right?
Yes.
So the algorithm can sort of push a button and then you get sort of a sample which is chosen from distribution P or distribution Q, and then your goal is to distinguish, I mean, to figure out whether these samples come from distribution P or distribution Q. So now I wonder, I mean, what does a quantum distinguisher get to see from one or the other distribution? Does he also get to see classical samples? I guess not. I guess he needs to have some stronger sort of access, some sort of superposition access.
Yes, completely. Yeah.
What does that now mean? Does he get a superposition of all the possible samples where the amplitude or the probabilities, well, square root of the probabilities?
Yeah, that's it. I think it gets a superposition of all the inputs. Yes.
But I'm confused because you're speaking of inputs, right? It is, there are no inputs, right? You get sort of a sample, or.
Well, when I mean input, I mean
it's not a function, right? The function has an input, right, and produces an output, but the distribution produces samples. So I'm confused when you speak about the superposition of inputs.
So if we have a look at the encryption case, no. Sorry, I'm actually search. I'm not sure I understand the.
Sorry. Right. I mean, you were talking about sort of a algorithm, a quantum algorithm that can distinguish a non-biased from a biased distribution.
Yes.
Sort of my question is, what sort of access? I mean, of course, somehow the algorithm needs to get information from the distribution. I mean, from one or the other. So my question is, what sort of information does the algorithm get? Again, sort of, a classical algorithm gets samples from one or the other distribution, classical samples.
So the classical one has queries, right, to an encryption oracle? No. Yeah, the classical algorithm queries an encryption oracle?
I mean, not if we're talking about an algorithm that distinguishes one distribution from another. So I'm not sort of thinking about using this algorithm to breaking some encryption scheme, just sort of thinking of an algorithm that is supposed to distinguish a uniform distribution from a biased distribution.
Yes.
Right.
Okay, so the question is, what is the input of the algorithm?
That's maybe one way to phrase it, or what sort of information or what kind of information does the algorithm obtain from the distribution? again, sort of classically, you obtain samples, right?
For example, like what I would guess you would get was something like you push a button, and from distribution P, what you would, I guess, would get would be like a coherent superposition of all possible samples. Is that
yeah. I mean, that's sort of what I was suggesting as well, right? To get sort of a state that has sort of as amplitude all the square roots of the probabilities from the distribution. Is that sort of in line what you're saying, Fred, as well?
Yeah, well, that seems like it's the only way I can think of. But
okay,
like
yeah,
the way to interpret it, but I don't know.
I think
okay, good. And we can also
there is another way, because you could just like enumerate samples. You can just have, say, on input 1 you get a sample, on input 2 you get a sample, on input 3 you get a sample, and then you get superposition access to these 1, 2, 3, 4.
Also, you have multiple distributions somehow.
No, always from the same distribution, but you just have independent samples depending on the input you give. And you could have like superposition access to that. I know this has been tried before, but I don't know.
But I mean, in a way, that's sort of what I'm asking, right? Because you could think of different ways to get sort of superposition access to a distribution. It's sort of not clear to me if, I don't know if they're all equivalent or not. But we can also maybe talk about this some more offline in case there's some more questions.
Yeah, which there is. There's another question by Shu Kao. Maybe we can unmute him. So you should be able to talk. Okay, or yeah.
Okay. So my question is that is there a quantum speedup for nonlinear cryptanalysis?
Sorry, is there a common speedup?
Yeah, for nonlinear cryptanalysis.
Yeah, a quantum speedup.
You mean beside the ones I talked about, or?
For non-linear cryptanalysis.
So yeah, so in the talk, you mainly talks about some linear cryptanalysis. So I'm wondering, so for non-linear cryptanalysis, are there some other similar results for some quantum speedup, some strong attack using?
Okay, so you mean non-linear cryptanalysis?
Yes, yes.
Okay, so it's true that non-linear cryptanalysis is less. So you mean using a non-linear approximation, right?
Like differential cryptanalysis.
Okay. So yes, so differential cryptanalysis, I think so we also propose some versions in the same paper as in the linear one. And the thing is that with linear cryptanalysis, there is this final magic, the kind of very nice trick to accelerate and improve the key recovery complexity that you don't really have in differential cryptanalysis. So there are some quadratic speedups in differential cryptanalysis that we proposed before, but so I was particularly interested in improving this last step of the key recovery of linear ones, because I think maybe there are some surprising things to do regarding quantum attacks. I'm not sure if I answered your question. If you can develop more, if you want more information.
Yeah, I think that answers my question.
Okay, thank you.
Okay, great. So I don't think there are any more questions. So I'd like to thank Maria again.
Thanks.
A bit, and so she'll be available for any further discussions in the meet and greet room. And otherwise, we reconvene at 2:30, so in about 25 minutes. Thank you very much.
Thanks a lot for the invitation. Thank you.
To share my slides.
Yes.
You should now, right? Full screen.
We don't see them full screen yet, but yeah, that's good. I think, yeah. We're ready to go, Margarita.
Okay. Welcome back, everyone, for this afternoon session. Before we start, just a quick reminder on how to ask questions. If you have any questions, you can either use the Q&A feature in Zoom, or you can raise your hand. And feel free to ask your questions during or after the talk. The first talk of this session is an invited talk by Alex Grillo on quantum zero knowledge from locally simulatable proofs. The floor is yours, Alex.
Thank you very much for the introduction. And this is a joint work with Anne Broadbent at University of Ottawa. And this result is, it lies in the intersection of these three different fields: quantum information theory, cryptography, and theoretical computer science. So in order to slowly get into our result, I'll first try to define the basic notions of these topics before getting to the details. And in order to start that, I'd like to start with the notion of interactive proofs in theoretical computer science. So, a lot of you might know, like we can define problems by we can group problems in complexity classes to define its hardness. And the complexity class NP tries to model the problems that are easy, whose solution is easy to verify. So in order to be a bit more precise, we say that a problem is in NP if there exists a polynomial time algorithm that we call V, or the verifier, that receives some help, untrusted help from the prover, and decides to accept or reject. And here the idea is that the verifier wants to prove some statement, and for true statements, there is a proof that convinces the verifier that the statement is true. Or if the statement is false, no matter what the prover sends, then the verifier should reject, should check that this proof is wrong. And the concept of NP is a cornerstone in complexity theory. And given its importance, it was also extended to different settings that have had fruitful applications. And one of these extensions is the complexity class IP. And here we still want to prove truth or false, like to prove that statements are true, but now we're also given the power of interaction. So here the verifier communicates back and forth with the prover. And after this communication, this verifier should accept or reject. And again, we want for true statements, there exists some strategy for the prover. So there is a set of messages that the prover might send that makes this verifier to accept. And for strings for false statements, no matter what this prover does, this verifier should reject. And actually, this power of interaction gives a lot of computational power to this model, because we know that this is equivalent to all problems that can be solved in polynomial space. So we strongly believe that the given interaction to a proof system strictly increases its power. But then to cryptography, just interactive proof systems are not sufficient. So we require more properties from these proof systems. And one very useful property is what we call zero knowledge. So again, we assume that you have this interactive proof system, but now we want to prevent the verifier from learning secrets from the prover. So the idea is that at the end of the protocol, the verifier didn't learn anything. But this is a bit, this is the rough, definition. So in order to be more precise, we need to add more objects into this set. And and also as we want to hear that the verifier does not learn anything, we kind of think that this verifier is malicious. So we think that the verifier might behave dishonestly in order to try to learn as much as she can from the prover in order to gain information that she was not supposed to have. And we have that this polynomial time verifier should also output some, it interacts arbitrarily with the prover and then outputs some object that has some distribution X. So with the output of this malicious verifier has some output, like it's a random variable. And in order to show that this protocol is zero knowledge, the formal definition is requiring the existence of simulator that is also polynomial time, but does not talk to the prover. And this polynomial time simulator also has output some random variable y. And in order to say that this protocol is zero knowledge, we want to say that y and x cannot be efficiently distinguished. Because if they cannot be distinguished, then the verifier could show up this value x that she has, but this could have actually been cooked up without talking to the prover. So that's something that does not require the secret that the prover has. And in order to formally define this, we require that any polynomial time algorithm, A, it cannot see the difference when it's given some x that's drawn from the first distribution, or if it's given some input y that's drawn from the second distribution. So we want that whenever like this algorithm should behave exactly the same, regardless of or almost the same, regardless of these input distributions. And this notion has been, as I said, fundamental to the notion of like it's a fundamental notion in modern cryptography. I don't know if there's any question, like if there are any questions now, but I have an example. So zero knowledge is usually something that like it seems too powerful to be true. So I'd like to first give an example of zero knowledge protocol, and then maybe we can open for questions on this topic if there is any. And the canonical one of the canonical zero knowledge protocols is for the problem free coloring. And here the verifier has as an input some graph, and the verifier wants to know if there is a way of coloring this graph with only 3 colors in a way that every edge only touches two nodes with different colors. And let's try to have an interactive rule system for that. So the prover is unbounded, so it's very powerful and can iterate over all the colorings and find if there is any coloring that satisfies this property. And the prover could just, for instance, just send this coloring to the verifier, and the verifier could check if all the colors have the correct property, like two nodes with that are adjacent, they don't have the same color. This protocol is complete, meaning that if the graph is 3-colorable, the prover can convince the verifier. It is sound because if the graph is not 3-colorable, if there's no such coloring, no matter what the prover sends, the verifier can check if this graph is 3-colorable or not. But this protocol is far from being zero knowledge because the verifier is learning the coloring, and this is not something that we expect it to be done efficiently by this verifier. So we have to propose, we have to change a bit the protocol. And for the protocol, so instead of the prover sending this coloring to the verifier, the prover will just permute the colors, and this is more of a technicality. But then this prover will put each color into a safe, and we'll send each of the safes to the verifier, but we'll keep the code to open them. So the idea is that, okay, the prover writes on a piece of paper and you can imagine it as this. The prover writes on a piece of paper and send all the safes to the verifier. The verifier then picks one of the edges informally at random and asks the prover, give me the code to open the safe, the corresponding safes of this, for instance, of this edge. And the prover then sends, okay, I'll give you the codes that open both safes. And then the verifier just opens it and checks if the 2 colors are different. In cryptography, this safe is what we call bit commitment, but for this talk, like during this talk, I'll keep this with this analogy of safes for simplicity. And now this protocol is complete because, again, if the graph is 3-colorable and the prover behaves honestly, then the verifier always see 2 nodes that have a different color. The protocol is sound because if the prover sends a coloring and the verifier opens one of these red uniformly at random, then with probability, with some probability, with no negative probability, this verifier will open the boxes that contain the same color because there's no way that they all have different colors. And now, more importantly, this protocol is zero knowledge. And I won't prove this formally, but the intuition is that everything that's in the safe is not known by the verifier. And the only thing that the verifier knows is that when he opens the 2 safes, he sees 2 different colors. So we could simulate this this distribution by putting an arbitrary color in each safe. and then just coloring this one edge with two different random colors. So this is very rough and maybe too fast, but this is the intuition why this protocol is zero knowledge. And then we, since through coloring is an NP complete problem, we now have a zero knowledge for all problems in NP. So yeah, I don't know if there is a question now.
There is no questions, but there is a comment from Gilles Brassard. He says that for those who might not know, it would be useful to say that the indistinguishability of X and Y only has to hold on yes instances.
Oh yeah, that's a very important. Thanks, Gilles. Yeah, the zero knowledge property only holds when there is some secret to be hidden. So, for instance, if the graph is not through colorable, then we don't care about anything. We just care when there is a through coloring that to be hidden from the verifier. So this protocol is completely classical, but we're in QCrypt, so we have to go to quantum. So now we go to since all of these proof systems, they have been very important in classical cryptography and computer science, we also have defined the quantum version of them. And in particular, we have the quantum version of NP that we call QMA. And here we have a quantum proof system where this verifier, that's a polynomial time quantum algorithm, receives from this quantum prover a quantum proof that will help him to verify if a problem is in the language or not, or if it's a yes instance or no, or as I said before, if the statement is true or false. And again, we want that for true statements, there is this quantum state that the prover will send to the verifier that will make this quantum algorithm to accept with high probability. Or for false statements, no matter which quantum state this prover sends, this verifier should reject with high probability. And again, with we can add interaction into these proof systems, and now we can define the complexity class QIP, where the verifier and the prover they can send quantum state back and forth, and at the end of the day, the verifier should accept or reject, and the acceptance and rejection probability is what we expect it to be, extending the previous results. We also have the QIP is equal P space, so this we also expect this complexity class to be much more powerful than just a single shot quantum proof. But again, for cryptography, this might not be sufficient, when we also might require other properties such as quantum zero knowledge. So now we can extend this notion also to in the quantum setting. And as before, the verifier is a quantum algorithm, but now this verifier could be malicious and try to deviate from the protocol to learn as much as she can from the prover. So she might, so that's why we assume that it could be malicious. And then at the end of talking, after talking to the prover, this verifier outputs some quantum state row. Now we don't need to have, the probability distribution, the random variable is somehow in the mixture of this quantum state row. And as in the classical setting, what we want now is to have a simulator that might depend, of course, in this malicious verifier. And this simulator, again, does not the prover, but outputs some quantums, is a quantum algorithm that outputs some quantum state sigma. And the quantum zero knowledge protocol means that for yes instance, so for true statements, rho and sigma, they cannot be distinguished. And this again means that for any polynomial time quantum algorithm, this polynomial algorithm should behave almost the same if she was given the reduced the density matrix rho or the density matrix sigma. So now let me describe a bit the landscape in zero knowledge for quantum proof systems, or for QMA and the complexity class that I defined. And using a lot of complex theoretical results, we already knew that there exists a quantum zero knowledge protocol for QMA. But this protocol is very inefficient, like from the perspective of the prover, and it is complicated. And actually, we don't have using these complexity classes inclusions, we lose all the intuition about this protocol, and we actually, I think, we don't have it written down. It's something that is just a matter of complexity classes. It's just a theoretical result. Until in 2016, Broadbent, G, Song, and Watrous, they finally show a protocol for a zero knowledge protocol for QMA, for quantum proofs, which is much more intuitive. So it uses the structure of this QMA proof system, and in particular, they have a protocol that if the prover of the zero knowledge protocol is given the QMA proof or the QMA witness, then the prover only needs to run, the honest prover only needs to run in polynomial time. And that's a very desirable property for cryptography. But again, this protocol, okay, it's much better than this previous more complex one, but still it's not as simple as the zero knowledge protocol through coloring that I show. So it needs much more crypto, it needs more complication, more rounds. So it's not what to expect from the nice textbook protocol for zero knowledge for QMA. And then finally, last year with Broadbent, we explored some technical tools that were developed in my result with Sloths and UN. And we finally show a very simple protocol for QMA. And this is the same style of protocol as the one for through coloring. So it's the one that the prover commits to some information, the verifier performs a random challenge, and then the prover answer or open some of the commitments that were done in the first round. We also have some variations of this result. Because of the time limits, I won't discuss much about them. But also an interesting thing is that we have other applications that are also for complexity theory, and actually some of these applications are the ones that enable us to have these zero knowledge protocols. And in particular, we finally show the QMA hardness of a problem called the consistency of local density matrices. I'll define this problem more precisely in the next slide. But this problem was open, it was not known if this problem was QMA hard since Yikai Liu defined it in 2006, I think. And for the rest of this talk, I'll give a bit more details on this problem on consistent local density matrices and how we can have simple zero knowledge protocols from it. And then I'll give some ideas that allow us to prove the QMA hardness of this problem. But and it's not just because this is not just for complexity theory. These ideas, they might be useful somewhere else. Like I think this is a tool that could have other applications. So if there's no question, I will switch gears and start talking about consistent local density matrices.
Yes, no questions at the moment.
Okay, thanks. And this problem is the following. So imagine that someone gives you a lot of pieces of quantum state. So someone gives you a lot of local density matrices on, let's say, 6 qubits. So you have the density matrix rho 1, rho 2, up to rho m, and they might intersect, like they do intersect actually. And then you want to know if there is a global quantum state that here are called psi. So if there is this global quantum state, whose marginals are consistent with all of these local density matrices. So more formally, we ask is there this this global quantum state psi, such that all these reduced density matrix, the matrices are close to the rho i's, like the inputs that you had, up to some negligible epsilon. Or on the other hand, if no matter which quantum state you have psi, there must exist one of these density matrices such that the reduced matrix of psi on the corresponding qubits is very far from the density matrix on 6 qubits that you had before. So there is an inverse poly gap between this distance is at least an inverse polynomial. As I said, in 2006, Liu defined this problem, and it proved that this problem is in QMA. So it shows that one can prove that there is a quantum state that that allows us to check if the margins are consistent. And this containment is actually somewhat simple. So the quantum proof is the most natural one that you can think. The quantum proof is just the quantum state that is consistent with all the local margin or with all the local marginals. It's not as simple because actually you have to give a lot of copies of this quantum state psi. So the proof is, let's say, a lot of copies of psi. And in order to verify that the marginals are consistent, one can use some sort of tomography. So you can do tomography on the local parts of these copies of psi and check if it is consistent with the row-wise. So there are some technicalities that are not in order to this proof system to work, you have to deal with some technicalities, but I don't want to talk about this now. Like I assume that, for instance, all the copies are intentional product and so on.
Alex, sorry to interrupt you. Just a quick question on this slide from Gilles Brassard. Which norm are you using to compare density matrices?
The trace norm. So Liu proved that this problem is in QMA, and he had some partial results to prove that this problem is actually QMA hard. So it encompasses all problems in QMA. Also, or on the other hand, you can use this problem to describe all problems in QMA. But as I said, since then it was an open problem to fully prove that it's QMA hard. And as I said, with broadband, we finally showed that this problem is QMA hard. And this is very important because now it allows us to, for instance, give a zero knowledge protocol for this problem. And once you do that, you have a zero knowledge for all problems in QMA because now this problem is a good representative of this complexity class. And before explaining how we prove this QMA hardness, I'll first show like the protocol, the zero knowledge protocol is actually very simple once you have this result. And I'll next, now I'll explain how the zero knowledge works, or how the zero knowledge protocol works. And here, as I said, the input that the verifier has is this description of this local density matrix, rho 1 up to rho m. And as I said, in the original QMA verification, the prover is supposed to have a lot of copies of the state that's consistent with this local density matrix. And the protocol works as follows. The prover applies a quantum one-time pad on this state and keeps all the one-time pad keys. And if you don't know what the one-time pad key is, you just apply random Paulis and you keep the Paulis, like you keep returning the Paulis. And the point is, if you only have the first state, you have the total mixed state and you have no information about what's encrypted. And now we need to use a bit of cryptography. So as in the original, like in the zero knowledge protocol for three coloring, the prover will put each of these one-time pad keys in the safes and send everything. So sends the state and all of the safes to the verifier, but again, keep the codes, the code, like, or the password to open the safes. And since the verifier cannot see what the code is cannot see what the one-time keys are, because they are because of the property of the safe, you cannot see inside the safe. Then this quantum state is totally unknown to the verifier. So it's the totally mixed state, and the verifier has zero information about it. Then in this protocol, the verifier just says, okay, I want to check if the state that you sent me is consistent with the ith density matrix. And then the prover gives the codes that open the safes that reveal the one-time keys for the qubits corresponding to the density matrix ROI. Once the verifier has this information, has those one-time pad keys, the verifier can undo the one-time pad, and then she's supposed to have the raw qubits, like the raw qubits of psi on the corresponding qubits of the density matrix ROI. And once she has removed this one-time pad, she can run the same verification that she did in the original QMA protocol. So from the properties of the QMA protocol, we have that this protocol is complete and sound, and also about properties of the safes or in cryptography bit commitments. But also now the thing that we're gaining is that this protocol is now zero knowledge. Why? Because the only thing that is outside of the safe, so everything that the only part that the verifier knows about this quantum state is the qubits corresponding to the density matrix ROI. But the verifier, if again, this only works for yeses, so it only works when there is a state that's consistent of these local density matrices. But if this is the case, the only qubits that the verifier has on the clear without the one-time pad key are completely known by them, because he had the description of the states, like he had the classical description for ROI. So the intuition here is that the verifier is not learning anything about this state psi, because he knew the marginals already. And of course, the problem is how they connect to each other, and this is still not known after the verifier runs this protocol. And then this is just the intuition level. So we can formalize it and provide a simulator whose view will be indistinguishable from the view of the verifier in this protocol. Now I'll tell a bit how we can prove that this problem is indeed QMA, the consists of local density matrices is indeed QMA hard. And the idea is to use error correcting codes. So for instance, let me explain or define things by example. So imagine that you have the STEAM code. So the STEAM code maps the qubit 0 and this logical qubit 0 into this physical qubit here, or physical state here, and this qubit 1 here to this physical state here. And if you have some quantum state psi, and you consider the encoding of the psi, so we have 7 qubits that encode this logical 1 qubit psi. We can do by inspection that if someone asks you, like gives you 2 positions of this code word, so gives you asks you what's the reduced matrix of this code word on these 2 qubits, you can compute it very easily without seeing psi, because by inspection, for every reduced density matrix on 2 qubits of the STEAM code, you have the total mixed state. So in particular, there is a very efficient algorithm that gives you I and J and computes the trace of this encoding of any quantum state psi or any qubit psi on the qubits I and J, because this algorithm just output identity. But unfortunately, this is not, okay, things are not, these are good, but not great for now, because if someone gives you 3 qubits, then one cannot compute these density matrices efficiently. And one can see that, for instance, even for 0 and 1, this depends on the qubit being encoded. And the idea is that, okay, because 3 is bigger than the distance of the code. So this is, okay, this is the technical problem that we have here. But then when in this work with Lofstra and Nguyen, we define this notion of as locally simulatable codes. And what we show is that these distinct codes are S locally simulatable. So, and the idea here is that we want to do the same thing that we did with the normal string code. So we want to simulate density matrices of code words, but now for a bigger number of qubits. And what we show that if you fix an S and you pick a big enough concatenation of the string code, then first you can compute the density matrix on any set of S qubits of an encoding of some state row encoded under this correcting code. So the same thing as discussed before. But we have also something stronger. We can show that you can compute the density matrix of the snapshot of computation on these code words. So also explaining by example. So imagine that you have the encoding of some qubit row. And we have, for instance, for the properties of the string code that you can apply Hadamard's transversally. And what we show is that for every snapshot, so for every snapshot of the computation, we can also compute the reduced density matrix, the S reduced density matrix of this snapshot. Okay, so this is this simulatable codes notion that we use in order to prove this QMA hardness. And let me now also describe in more details how we prove hardness. And one of the second key idea is to use this the famous circuit to Hamiltonian construction by Feynman or Kitov, depends how you see it. And the idea is that from this circuit to Hamiltonian construction is that when you can start with a quantum circuit, let's say that that is decomposed, let's say in gates U1 up to UT, where each gate is, let's say, 2 local. So you have 2 qubit gates. Then you can define some Hamiltonian HV. And if you don't know what a Hamiltonian is, it's not so important, but the idea is that this Hamiltonian fixes some state that we call the history state. And this is the state that contains a superposition for every snapshot of the computation on V. So, or in other words, so you have the superposition of every time step from 0 to t, and you have some clock register that tells, okay, this is the snapshot at time t, and this is a stage of the computation at the tth step. So the idea is that this Hamiltonian, that like this object that you construct, will somehow pinpoint this state that you call the history state. And the acceptance probability of this verification circuit is related of how good this history state will be in respect to this local Hamiltonian. And the idea that we have in order to prove this QMA hardness of consistent of local density matrix is now tweak a little bit this verification circuit in a way that when you consider the history state of this new verification circuit, this new verification circuit is simulatable. So one can efficiently compute the reduced matrix of this new verification circuit, and this is the then this would be this consistence of local density matrix instance that would be corresponding to this QMA verification. So let me give you a bit more of details. So when you start with this QMA verification V, again, it is decomposed on these gates and has this quantum proof sign it. In this, we now want to construct a new quantum QMA verification system, V prime, that instead of receiving this initial state sign it receives a more complicated one. It will receive the one-time pad of this circuit, along with the one-time pad keys. And again, like this one-time pad keys and the one-time pad inside this here is a bit for technical reasons. But the important part here is that everything here is encoded under a simulatable code. Then this new verification V prime will do some extra steps. So for instance, check if the encoding of every qubit here is correct. will, under this encoding, undo this error correcting code, create encoded the auxiliary bits, and then perform the original verification here, but on this encoded state, either by doing transversal gates or by doing, let's say, T-gadgets. So we borrow from these techniques from fault-tolerant quantum computation in order to do universal quantum computation inside this encoded state. After doing this, the verifier has the encoded output, and then the verifier can just decode it and decide to accept or reject. So what we're able to, so then in this work with N, what we're able to show, there exists a classical algorithm that can compute in polynomial time the description of all reduced matrices of the history state of this new V prime. And this algorithm cannot, of course, this polynomial time algorithm cannot decide the QMA, so it works for both yes and no instances. But what we're able to show is if there is, once you compute these local density matrices, there exists a global state that's consistent with them, if and only if it was a yes instance for the QMA problem. So I think I'm a bit out of time, right?
Yes, it would be nice if you could wrap it up.
Okay, so I'll skip a little bit the sketch proof and I'll leave it for the questions. Another thing that I'd like to highlight is that in this work and in a concurrent work with Michael D'Angelo, Vidic, and Zhang, we also define the notion of proof of knowledge. Is that this is a notion that tells that not only the prover has it's a protocol that not only makes the verifier accept or reject, but it also, if the verifier accepts, she knows that the prover indeed has the secret, so indeed has the quantum witness. But I'll also leave this for the questions. And I'll just want to finish with some interesting opening questions, of course, in my point of view. So one embarrassing question that I've been asking a lot, maybe I should try harder to solve it. So we know that classically zero knowledge is very influential and very useful in different settings. And we don't have too many applications for quantum zero knowledge. So can you use these quantum zero knowledge protocols to build other quantum primitives? So some primitives in quantum cryptography. An interesting question is that we know zero knowledge works well in the quantum setting, but how about in the no signaling setting? So do you have that non-signaling interactive real systems? They are also closed under zero knowledge. And then we'll have more technical questions that I think I'll leave for now, and thank you for your attention.
Thanks a lot for your very nice talk, Alex. So now we have some time for questions. At the moment, we don't have any questions in Q&A. So, okay, we have one. Question by Gel Don. In your ZK protocol for the consistent local density matrix problem, the prover might hold only a single copy of the witness state, and it has to send this state, encrypted with a one-time pad, over to the verifier. Does this mean that it can only run a single execution of the protocol? Do you consider this a weakness of the protocol?
Yes, it is. I think it's a weakness. I'm not sure if it's a weakness of the protocol or of the setting. So the question is, you're completely right. So we cannot reuse these quantum states. But maybe one thing that one could try to show is that this is inevitable. And this could indeed be the case, right? Because even for QMA, you also have this same type of argument, right? So if the prover only holds one copy of the QMA witness, and when this prover sends it to the verifier, then the prover, it has to find again this same quantum state. So it's not easy to copy, right? So we don't expect that quantum proofs can be easily copied. So it is a weakness of my, so just to wrap up. So I think it is a weakness of my protocol, but it could be just a weakness of the model.
But that's still an open problem. Whether
That's an open problem. Yeah. So this is an open problem if this is inevitable.
I mean, it could even be useful in some settings, right? To be restricted to only proving once.
Exactly. So when you use non-clonability of proofs to do something, yeah.
Yes, thank you.
Thank you. So there is another question from Christian Schaffner. Do you want to ask it yourself?
Yes. So I was just wondering, when you define the simulator, I mean, it's clear to me that it works for honest verifiers, but do you run into any issues if you consider dishonest verifiers?
No. It works for dishonest. So if you're used to zero knowledge in the classical setting, then we don't talk about transcripts. It's just about like the malicious verifier interacts with the prover and then outputs some quantum state. And the idea is that the simulator is able to run. Okay, the idea is that the simulator is able to run this verifier, this dishonest verifier, in a black box and outputs another quantum state sigma. And then what we want to show is that for every polynomial time malicious verifier, these two quantum states are close, or sorry, are indistinguishable.
Right. Yeah. Okay. And the simulator just does the same as the dishonest verifier would do, basically.
Yeah. No. Yeah, it tests. Yeah, it somehow uses. Yeah, whenever the verifier has to do some computation, he asks this in a black box to this malicious verifier to run it. Yeah.
Okay, is there any more questions?
Yeah, I'd like to follow up on the simulator question, because even for an honest verifier, it's not fully clear to me why it is zero knowledge. But sort of the intuition is that the state that he gets, sort of the part of the state that gets decrypted, is sort of the state that is anyway described by one of these row i's. Right, that's the intuition.
So okay, I can okay.
But sort of my question,
I'll give you the simulator for the honest case.
Is efficiently producible, given the description.
Yeah, because because it's a 6x6 matrix, so you can do that. Like the point is, this qubit, like this reduced matrix has constant size.
Oh, okay.
And then it can be efficiently computed.
Okay, yeah, makes sense. Thank you.
Okay. Thank you very much, Alex. We have come to the end of this session, and now we move over to meet and greet. If you would like to ask any further questions to Alex, I invite you to join us there, and then we can continue these discussions. So thank you.
Thank you very much, everyone.
Okay, shall we begin? Okay, guys, so welcome to the session on encryption and coin flipping. We have 3 talks. The first one is on quantum encryption with certified deletion. It's going to be given by Anne Broadbent. So Anne, I'll pass the floor to you.
Okay, hi everybody.
This talk is on quantum encryption with certified deletion, and it's based on joint work with Rabib Islam. So I want to start with a physical analogy to the scenario that we're going to be looking at today. We consider Alice places a message into a safe and locks that with a combination and sends the safe to Bob. At that point, Bob has an option. He could choose to return the safe as it is in this closed state to Alice, in which case Alice would be convinced that Bob did not open the safe and to read the message. Or he could keep the safe and when the combination is revealed, open and read the contents. And this is actually an exclusive OR. In the physical world, he could do one or the other, but not both. And here, when I talk about the combination being revealed, Alice could simply broadcast it. So the question is, could we achieve this type of functionality in the digital world? And the answer is a resounding no, at least if you're looking at encodings using classical information. So here's a simple proof by contradiction. Say Alice encodes a message using a key K and sends that to Bob. Then Bob can make two perfect copies. With the first copy, he could convince Alice that he did not read the message. And with the second copy, he will wait to receive the combination and open and decrypt. So what we're going to do today is we're going to show how quantum mechanics enables the best of these physical and digital worlds. Namely, we'll give an encoding for a classical message into a quantum state such that Bob will be able to prove that he deleted the message by sending Alice a classical string. And this is what we call quantum encryption with certified deletion. There's some related work here that I unfortunately don't have the time to go into details right now. I wanted to give you an idea of the scheme via an example. So here we're going to be encrypting a message of 2 bits. And in order to do that, we sample first theta, which is 4 random bits. We sample R, which is also 4 random bits. And then we create the Wiesner encoding, which is the string R in basis theta. So when the theta is 0, we encode the bit R in the computational basis. And when the bit theta is 1, we encode R in the diagonal basis. Sorry about that. Okay. And then let R comp be the substring of R, where the qubits are encoded in the computational basis, and R diag be the substring of R, where the qubits are encoded in the diagonal basis. The encryption of M will therefore be the Wiesner states together with M XOR R comp. So from here, if Bob wanted to delete the message, he would simply measure all qubits in the R sub theta in the diagonal basis. And this would give him a string, if he's honest, with 2 wildcards. These would actually be uniformly random bits and two deterministic bits, namely the substring R diag. In order to verify deletion, Alice would simply check that when theta is equal to 1, the positions of this string are consistent with R diag. To decrypt using a key theta, Bob would simply measure all the qubits in R theta and only look at the substring R comp. And then using the value of R comp, he can, as well as the classical part of the ciphertext here, he could deduce M. The proof intuition is, well, one that is present in a lot of quantum cryptography. So basically, as the probability of predicting this diagonal basis string increases, that means that the adversary is good at producing a proof of deletion. The probability of predicting the R comp bit string decreases. So that means that the adversary becomes unable to decrypt even given the key. So another way to think about this is that if Bob wants to be really good at convincing Alice that he deleted, he should really measure all the qubits in the diagonal basis. But measuring a qubit that was initially encoded in the computational basis, in the diagonal basis, will effectively erase that part of the information. So this entropic uncertainty relation is underlying here the intuition. This is the entropy. and C is the maximal overlap of the observables. Here's how we define the security of our scheme directly applied to the scheme that we're looking at. So we consider Bob to be adversarial, and he chooses a message, sends that message to Alice. Alice chooses a key as well as a random bit B. Based on B, Alice will either encrypt the 0 message or the message that Bob sent, and she sends that back to Bob. Bob then produces Y, which is the candidate proof of deletion that Alice verifies using the key, and that makes her accept or reject. Then Bob is given the key, theta, and then produces a bit B prime. And then he'll win the game if and only if the bit B prime is equal to the initial bit B. That is, he was able to gain information about the message. And we'll say that the scheme has certified deletion property if this probability of winning is close to 1/2. Just a quick outline of the proof. We will first consider the entanglement-based game, and then we'll apply some entropic uncertainty relations that have been initially developed in the context of quantum key distribution. There are refinements of this basic protocol. Namely, we'll do a noise-tolerant protocol by using error correcting codes. And we'll also reduce and make uniform the advantage that the adversary has here by using privacy amplification. So we give an upper bound on the max entropy. This gives us a lower bound on the min entropy. And then we're able to give the full security of this protocol. So in summary, we have a classical proof of deletion. It's prepare and measure because we're sending and measuring single qubits, and we have noise tolerance. Thanks a lot.
Great, thank you so much for your talk, Anne. The next speaker is Wei. He's going to be talking about on security notions for encryption in a quantum world. So the floor is yours, Wei. Feel free to share your screen.
Okay, sorry. So hi everyone. So today I'm talking about our paper on security notion for encryption in a quantum world. This is joint work with Céline Chevalier and SNL Primary. So usually when we talk about standard security or even post-quantum security, we assume that the adversary are either classical or quantum, but he only has classical communication to the honest party or classical access to the primitives. So we can go one step further when we can consider fully quantum security, in which the adversary not only have quantum computers, but also have quantum access to the primitives or the honest parties. So this motivated by scenarios such as running classically obfuscated programs in quantum computers. So in our paper, we focus on studying fully quantum security for classical encryption. So previously, this lab work was started by Bonnet-Zandri in 2013, in which they give the first security definition for quantum security, which allows quantum learning queries, but only classical challenge query for both public key and submit key with chosen ciphertext security. And in 2016, Gagliardini, Hunsing, and Strapner give another security definition, which allow quantum challenge queries, but they are restricted to a special minimum oracle. So basically, the minimum oracle has only one register for both input and output, while usually in this standard oracle model, we have two different registers, one for input and the other for the output. And also the definition limited to symmetric key encryption with chosen plain text security. So the open question is to define security notion which allows quantum challenge query in the standard oracle model, both for public key and symmetric key encryption with CCA security. So in the classical setting, the security is modeled by a game between the adversary and the challenger. And in the CCA security, the challenger need to be able to recall the challenge query from the adversary so he can prevent trivial attacks. But when we translate this notion to the quantum setting, It's difficult because the no cloning theorem. So now the chance could be some quantum state. So you cannot easily copy that. Or it's also because the measurement is short enough. And another reason is that because in a paper by Bonnet and Zandri, they give the impossibility for any left or right indistinguishability notion. So basically that in this kind of notion, the adversary can send out two messages, M0 and M1 as a challenge, and the challenger will encrypt one of the two messages. And so any quantum translation of this notion will be impossible to achieve. So in our paper, we answer this open question by giving us first achievable and meaningful chosen ciphertext security definition for public key and symmetric key in the quantum setting. So let me give you a brief overview of our technique. So first, to bypass Bonnet-Zandri impossibility, we switch from a left or right indistinguishability notion to a real or random indistinguishability notion. So this real or random indistinguishability notion has been studied before by Masajabi and Straff in 2016. And very recently by one of our authors, they saw that actually real or random indistinguishability notion is one of the strongest one we could achieve for encryption in the quantum setting. And to define chosen ciphertext security, we adapt a Zandri compressed oracle technique to randomize functions. So now you can consider the encryption of the randomize function. So using the recording technique, we can record the chance query, and then we can define the quantum notion for encryption similarly to the classical setting. So in our paper, we also give other results. So we saw that encrypted mechanism shows CCA is secure, similar to the classical setting. We give a compiler to convert any Bonnet-Zandri secure public key encryption scheme to our stronger security definition. And we also give the first definition for non-malleability in the quantum setting for classical public key encryption. That's all. Thank you.
Great. Thank you very much, Ray, for your talk.
Thank you.
Okay, and let's move on to the third speaker in the session. That's going to be Atul Singh Arora. The topic is analytic quantum weak coin flipping protocols with arbitrarily small bias. So Atul, feel free to share your screen and start whenever you like.
Okay, thank you. I suppose everything is in order, so I'll start. Okay, hi, my name is Atul. As already mentioned, I'm excited to present our work on weak coin flipping. This was done jointly with Jeremy Roland and Chrysula Vlahu. Right, so the coin flipping problem is the following. So there's Alice and Bob who wish to agree on a random bit by exchanging messages. And they don't trust each other and they want to arrive at a random bit at the end of it. So a variant of this problem is called weak coin flipping, where Alice wants a heads and Bob wants a tails. So this is known. In distrustful cryptography, it is the strongest known primitive, which can be done quantumly with information theoretic security, while classically it is impossible without further assumptions. And I should say that weak coin flipping is contrasted with the former, and the former is called strong coin flipping. So a coin flipping protocol is essentially any scheme of sending and receiving messages that solves the weak coin flipping problem. And obviously not all protocols are going to have the same security. The relevant figure of merit here is called the bias of a protocol, and it's denoted by epsilon, and it varies from 0 to a half. A 0 corresponds to a perfectly secure protocol, and a half means that the protocol is completely compromised. Okay, so perfect strong coin flipping was shown to be impossible by Kitaev, who showed that there's a lower bound on epsilon. Moshe, in his breakthrough result from 2007, showed that weak coin flipping protocols with vanishing bias actually do exist, but his proof was non-constructive. The best known explicit protocol until recently had a bias of 1/6. Last year, it was improved to 1/10. And in that same work, a numerical algorithm was proposed that approached zero bias. This left the status of weak coin flipping in a limbo. Is it solved? Is it not solved? And in this work, we sort of remedy this problem, and we give the first analytic solution to quantum weak coin flipping. All right. In this study, 3 equivalent frameworks were introduced by Kitaev and Moshon. The first uses SDP duality to certify the bias of coin flipping protocols. The second is called the time-dependent point game formalism. Here, one starts with 2 points, as shown in the graph, and these points are moved in successive frames by following certain rules, which are easy to state. The coordinates of the final point encodes the bias of the protocol. Finally, there's the time-independent point game formalism, and this is essentially a simplification of the point game formalism itself. It was in this formalism that Moshon proved his fundamental result, that is, weak coin flipping with arbitrarily small bias is actually possible. And this we can see by setting K to be arbitrarily large. So while these formalisms are known to be equivalent, the last step is non-constructive. Recently, in 2019, it was shown that numerically one can convert point games into explicit protocols, but no analytic solution is known. In this work, we give an analytic construction for converting Moshon's point games into explicit protocols. And this step can be understood as follows. So suppose we are given a point game and we focus on 2 frames of this point game, as denoted in the graph. This corresponds to applying some standard unitary, which is written in black, which is written in gray, and a non-trivial unitary, which is in black. This unitary is essentially specified if you can find the unitary that I have written in the blue box. So here, the unitary U has to satisfy 2 constraints, one equality and one inequality. The V here corresponds to the points of the point game, the weights of the points, of the initial frame. And XG corresponds to the weight, the coordinate of the initial frame, the points in the initial frame. XH similarly corresponds to the coordinates of the final points, and W corresponds to the weights of the final point. Okay, so that is the situation. So, okay, I'm sorry. I should mention here that. I'm sorry, I'm just messing up the slides a little. Okay, so what we want to do is, if we can find such a unitary U for every step of the point game, then we can essentially construct the required protocol. And this is exactly what we do for Moshon's point game. And the unitary looks something like this. I flash it in front of you just to show you that it's compact enough to fit in the slides. It's not overly complicated. Given the background of the problem, this is a good thing. But I can give you some intuition about it. So imagine you have some points PG, endpoints, which you're moving to another set of endpoints. Then the unitary that does the following. It sends V to W, which is the initial weights to final weights. Then it sends the product of the coordinates with the weights to the corresponding product in the final frame. And of course, removing the component along the previous vector. And this procedure is repeated with higher powers of the coordinates, the matrices XG and XH. And that's essentially it. It turns out that this construction solves the problem that we need. I thank you for your attention. And if you're interested, I invite you to look at the article and also consider looking at the longer version of the talk. Thank you.
Thanks, Atul.
Yeah, thank you very much to all speakers. And I'll hand the floor over to Or to head the Q&A session.
Yeah, we have time for a few questions. If someone in the participants would like, feel free to add a few questions. So Thomas Vidic had a question to Anne. Anne, is there a clear relation to other single-use quantum crypto primitives, such as quantum tokens by Ben David and myself, or one-shot signatures by Amos et al.? By clear relation, I mean some ordering between all these primitives in terms of which can be constructed from which.
That's an excellent question. Thanks, Thomas, for the question. In this case, I don't think we know the answer. It's a little bit different here because we're talking about, I would say, returning information and not using it at all. Versus decrypting and reading the information. So I don't see directly the link because there's nothing that you can kind of use, and it's more about that you can use once. It's more about returning or reading. But I think this is a good point. There's a lot to be done in understanding how these primitives relate to each other and what's the is there a basic primitive that could kind of link all of these together?
Okay, thanks. Thomas had another question to Atul. Either still a question of efficiency round complexity of this protocol?
Yes, so there was a recent result by Miller. First of all, thank you, Thomas, for the question. Yeah, so there was a recent result by Miller. I think it's this year in Stock. I think that was published, and it basically addresses this to a certain extent. It shows a lower bound on the number of rounds, and it seems to scale exponentially or doubly exponentially. I may be slightly wrong, but it's certainly inefficient. So it was shown that you cannot possibly do coin flipping efficiently. However, this was in the asymptotic regime. So maybe one can actually do coin flipping with epsilon, say 0.1 or 0.01 or something in a reasonable number of rounds. And that might be okay. Although I would be surprised if that happens to be the case, but it's open indeed. Thanks. I hope I answered the question.
Yeah, I can talk, right? Yeah. No, my question was just whether your protocol matches this lower bound. So
no, not at all. Not at all. No. There's a big gap. Yeah, it's much worse. Yeah.
Okay, thanks.
Yes. Thanks for the clarification.
We have another question to Anne by Ernest Tan. What are the main obstructions, if any, to extending the result to a composable definition? Since the protocol allows for the leftover hashing lemma to be applied, it would seem that it should be possible to certify epsilon indistinguishability from the ideal output.
Yeah, I agree. Our work here was focused on formalizing and achieving the first scheme to do this, but I actually think that our proof technique is amenable to composable definition because we could actually build a simulator out of it. So the only obstacle is to sit down and write this down.
Okay.
Thank you.
Thanks. Atul, would you like to ask the next question to Anne?
I think that's another Atul. I think there are two people with the same name.
Sorry.
That's not me.
Sorry.
Sorry.
So I don't know who that is, but there's another question by someone named Atul. Is it related to quantum bit escrow or cheat-sensitive bit commitment protocol?
Not that I know of.
I
don't know if someone wants to expand.
Yeah.
Can I ask directly or?
Oh, sure. Yeah. Go ahead.
Sorry. So in quantum bit escrow, there is like two conditions. One is binding and one is sealing, and they only achieve either one of them. So I was just thinking if this is related to it. But I mean, it's fine. I can maybe ask you offline.
Sure, I'd be happy to discuss. This, it's surprising that we can achieve this. It just it's super sneaky to just go around all the impossibility results. It's not exactly bit commitment. It's not exactly this. It's not exactly that.
Yeah, that's true.
So, but yeah, this is always interesting to explore.
Okay, thanks. Thanks a
lot. We do have some time to a few more questions. Maybe I could ask Atul. So one way I always wondered whether this is possible to construct weak coin flipping protocols is to use cheat detection for weak coin flipping, right? You could have a cheat that if you discover a cheating in one of the rounds, you immediately reject everything and stop. Right, and the question is whether there are any approaches to achieve that. Since you seem to have studied it carefully, then maybe you have any ideas regarding that.
Okay, so if I understand correctly, the formalisms that I've seen so far, basically motions and all of these, it seems that one can usually postpone first I should say that the cheat detection step is inbuilt into the formalism. So there's always this cheat detection step that happens. And when they try to generalize it, usually what they say is that, okay, you can postpone the cheat detection. So you can, even though you've detected it, you can somehow pretend that it's okay and you keep playing it. And in the end, you say that, no, you were cheating. And so therefore, I will not accept that you have won, something like this. So this is sort of inbuilt. I maybe have misunderstood your question. Maybe
sorry, maybe I could clarify. Suppose you had a protocol with some fixed epsilon, like with fixed bias, say 1/10, like a simple protocol.
Right.
Then you could run it in like 10 or n times in, say, in parallel or in sequence. It doesn't really matter. And if you detected the cheating in any of them, you would reject, right? And then you would maybe, maybe you would do a majority vote on the ones that, if there was, if the other person didn't try to cheat, you would simply do a majority vote. And that seemed like the intuition seems to be that this should work. And I've never understood what were the reasons why it does not.
So usually, I think the problem is that in weak coin flipping, we assume that there are two assumptions. At first, we assume that one player wants a heads and the other wants a tails.
Sure.
And when you have a string like this, so you're sort of doing like a string flip and then you're doing a majority vote. So there are two things. One is that the security proof is for just one round, assuming this is true. When you have a larger string, the strategy may be different. So a player may want to let you win a few times without actually biasing it and so on. So when you do the full analysis, it kind of turns back into the original problem, because you actually have to account for all quantum effects and so on. And then, so it's kind of general enough. I think maybe that, I don't know if that answers your question. We can discuss afterwards if you're, if you're interested. Yeah, I'm sorry.
Okay, thanks everyone. We'll reconvene at 4:30, right, in roughly 19 minutes. Shall we start? Okay, hi everyone. This is the last QCrypt session. The topic is post-quantum security, and we'll have, as usual, 3 talks back to back, and at the end we'll have a time for a Q&A. If you're interested, if you have any questions, feel free to type them now as we speak, and please mention to who the question is addressed, since we have multiple speakers. And we'll start with Yeledon. I hope I pronounce your name correctly. The floor is yours.
Thanks. Can you see my screen? Yes, thanks for the introduction. This talk is about the Measure and Reprogram Technique 2.0, multi-round Fiat-Shamir, and more. And this is joint work with Serge Veer and Christian Mayans. Our work is about proving Fiat-Shamir digital signatures, and in general, Fiat-Shamir zero-knowledge proof systems secure against quantum attackers, where by secure we mean secure in the quantum random oracle model. We extend the existing QRAM technique by Don, Veer, Mayans, and Schaffner to a larger class of applications, notably multi-round Fiat-Shamir signatures, bullet proofs, and sequential OR proofs. And finally, we also show that the security reductions that we get from applying this technique are essentially tight. While our result concerns a general QRAM technique, I'll start by explaining the main motivating example, namely multi-round Fiat-Shamir. There exists something called the 2n+1 round public coin interactive proof systems. These are a subclass of the zero-knowledge proof systems that Alex talked about, with a constant or logarithmic number of rounds, where a prover can prove its knowledge of some secret key to a verifier by sending a sequence of messages, the so-called commitments, upon which the verifier replies with a uniformly random challenge, and the prover sends the next commitment, etc., until he gets to the final response. But if we want to apply this protocol in a digital signature scheme, we need it to be non-interactive. In other words, we need the prover to send all of his messages in one go. And while now the prover no longer receives these random challenges from the verifier, he will have to compute them himself by taking the hash of each commitment using some publicly known hash function h. And publicly known so that also the verifier has access to it and can recompute these challenges and then check some verification predicate with respect to the sent commitments, the response, and the challenges produced by h. Now to prove security, or more precisely to show that this non-interactive scheme is as secure as the interactive one, we turn to the quantum random oracle model, where we model this public hash function h as an external random oracle to which all parties have quantum query access, which means that the function cannot be computed locally. So the adversary has to send these queries to the external oracle, but they can consist of a superposition of inputs. So when A makes a query, he actually sends a quantum state over to the oracle. Now, in many also classical random oracle model proofs, what we want to do is show the existence of a simulator that can simulate the oracle to the adversary, but also observe the queries. It might be that the simulator needs to know in which hash inputs the adversary is interested. But of course, observing a quantum state may cause it to collapse, and this may influence the behavior of the adversary, so that we can no longer in general predict what the output of the adversary will be, even though the simulator might need this output in the security reduction. But then comes our result on the multi-input reprogrammability of the QRON, which says that if we have this scenario where there is some adversary making Q quantum queries to a random oracle, before producing an array consisting of n different hash inputs and some additional output Z, such that some arbitrary predicate V holds of this Z, these x's and the corresponding hash values, then indeed there exists such a simulator which can pick n of the adversary's queries at random, measure them, and then upon the inputs that were found in the measurements, reprogram the oracle to some fresh random values theta. And it will then still produce some output x bar z bar, such that the same predicate v holds of this x bar z bar, but now with respect to the fresh random values theta. And this is for any particular choice of hash inputs x naught. And all of this at a loss at most order q to the power 2n. Now this technique is exactly what we need to prove that the advantage of the best adversary against the Fiat-Shamir transformed non-interactive scheme is at most order q to the power 2n times bigger than the advantage of the best adversary against the interactive scheme, which is what we needed for security. Thank you.
Thanks. We'll have a question at the very end. Our next speaker is Omri. The floor is yours.
Thank you all. I'm just sharing my screen. Okay. Okay, welcome everyone to this QCrypt talk on post-quantum zero knowledge in constant rounds. This is joint work with Nir Bitansky. So in this work, we are going to focus on the construction of a post-quantum zero knowledge protocol. So let's start with defining what exactly is a zero knowledge protocol. This is an interactive protocol between a prover and a verifier. We have an NP language L, and the prover would like to prove to the verifier that some instance X is in the language. Now, the first property of the formal definition is completeness, that asserts that if the instance is indeed in the language and both parties are ran honestly, then the verifier is going to accept. The second property is soundness, that says that if the instance is not in the language, then it doesn't matter what the prover is going to do, the verifier is still going to reject this false proof. And the zero knowledge says that a malicious verifier that tries to learn something interacting with the honest prover, it's going to learn nothing from the interaction. This is formally captured by the following definition. So there exists some polynomial time simulator such that for every polynomial time algorithm implementing the verifier, the output of the verifier at the end of the interaction, which captures everything that the verifier learned, is going to be indistinguishable, computationally indistinguishable from what the simulator is going to output. Of course, the simulator is not going to interact with the prover. So essentially, everything that the verifier learned, it could have just run the simulator and learn it by itself. So more specifically, this work is going to focus on zero knowledge against quantum attacks. That formally means that when protocols are run honestly, they are still classical algorithms, both prover and verifier, and completeness is perfect. If the instance in the language the verifier is going to accept, soundness is going to hold against polynomial time quantum provers, and zero knowledge is going to hold against polynomial time quantum verifiers, which means that now this polynomial time algorithm implementing the simulator is going to be a quantum algorithm, such that for every polynomial time quantum verifier, the now quantum state of the verifier at the end of the interaction is going to be efficiently simulatable by this quantum simulator. So what we know in terms of round complexity versus security type, whether it is classical or quantum, we know for quite some time how to do classical zero knowledge in constant rounds since the end of the 80s, and we don't know yet how to do quantum zero knowledge in constant rounds. And a small note is that this question was open even if we let the honest parties be quantum. So the results that we show in this work is that if we assume the existence of quantum fully homomorphic encryption, which is fully homomorphic encryption that can evaluate quantum circuits, and we assume also the hardness of LWE for quantum algorithms, we have a constant round post-quantum zero knowledge argument for NP. We also have what we call a quantumly extractable classical commitment, and these two theorems together combined with the previous work on zero knowledge for QMA, it implies the constant round zero knowledge quantum arguments for QMA. And one thing to say is that this work focuses more on the NP result. So few words on the main challenges of constructing a post-quantum zero knowledge protocol in constant rounds for NP. And the main problem is the no cloning theorem. So let's see why. So recall, how do we show zero knowledge? We need to show the existence of a polynomial time quantum simulator. And one more thing to recall is that the verifier is an interactive machine, which means that it has this inner memory that it keeps to itself, where it keeps tracks of all of the interaction and keeps all of its secrets. And this inner state plays a key role in the simulation. So in the classical world, traditional simulators are black box in the sense that they treat, we recall the simulator has access to the circuit of the verifier, but actually traditional simulator use this circuit of the verifier as an oracle. They treat it as an input-output function. They don't actually use the fact that they hold the circuit. And they are based entirely on the ability to clone this inner state of the verifier. Now, when we move to the quantum setting, this verifier is a quantum computer. Its inner memory is characterized by a quantum state, and we cannot just arbitrarily copy the quantum states that is the inner state of the verifier. And this is the problem with traditional simulator techniques, but more advanced kind of simulation techniques are called non-black box, starting with the work of Barak that actually treats the verifier as a circuit. It doesn't just use it as an oracle. It does more clever things, and it is a great question to ask. What about non-black box techniques? Are they useful to simulate without cloning? To simulate and show post-quantum zero knowledge. And unfortunately, they didn't work because one example is maybe they don't treat the verifier as an oracle, they do more clever stuff, but they still clone the inner state of the verifier one way or the other. And some of them, it's not clear that the quantum analog of these simulators would use cloning, but they definitely use tools that are not known for quantum computations. One example is universal arguments. And the question that we try to answer in this work, can we use the fact that a simulator holds the circuit of the verifier to perform this zero-knowledge simulation in constant rounds without cloning anything whatsoever? And the answer that we gave is that this is possible, and I won't have time to get into the techniques, so thank you very much for listening.
Thanks, Omri. Okay, so for our last talk, we'll have Chris.
Okay. Hi. Can you see my screen? Oh, good. Okay. Thanks for joining the last session of QCrypt 2020. This expository talk is about efficient simulation of random quantum states and random unitaries, and this is joint work with Gorian Alekic and Alexander Russell. Here's an overview over our results. We study the simulation of random quantum objects, so random quantum states and random unitary operations. And in this context, we develop a theory of stateful simulation. So we simulate an oracle, but we do this with an algorithm that keeps an internal state between queries. So for random quantum states, we achieve such a stateful simulation efficiently. And for random unitaries, we can at least prove that such a simulation is possible in polynomial space. Finally, as an application, we design a quantum money scheme that is unconditionally unforgeable and also untraceable. That's an additional privacy preservation property. To explain what I mean by stateful simulation, let's have a look at the example of a random function. So a random function from m bits to n bits is a very simple object, but exactly sampling it is infeasible as soon as the input length m is large. And therefore, there are several methods of simulating such a random function. So we study the oracle simulation problem. So we look at algorithms that have oracle access to such a random function, and we have a look, can we fool these algorithms into believing that they are interacting with an oracle for a random function instead of us who just simulate it. And for different limited scenarios, this is possible. For example, with t-wise independent functions, if the distinguisher is limited in the number of queries, or with pseudorandom functions, if the limiter is limited in runtime, if the distinguisher is limited in runtime. And the final line in this table is what the so-called lazy sampling technique. So here we don't have to put any assume any limits on the distinguisher, but the simulation is stateful. This is a very simple thing. We just sample the outputs of f one output at a time. And whenever somebody asks the same question twice, we look up in a table which answer we gave last time. Now the question is first of all, just to illustrate the importance of these primitives or of these simulation methods, here are some applications in classical crypto. So these are really very important applications of these simulation methods. One interesting question is, of course, can we do the same thing quantumly? So for example, for a random quantum state, so that's just a uniformly random state of n qubits. So we can maybe make a similar table. For example, exactly sampling it is completely infeasible because it requires an infinite amount of randomness. And also the other methods like the query limited case and the runtime limited case have been studied before. For example, by Jilu and Song, and also by Brakersky and Smurli. So they introduced pseudo-random quantum states. What we can supply now is the last row in this table, which is a stateful simulation method for random quantum states that works against any distinguisher. So we don't need to assume any limits on the distinguisher, but we pay for it by devising a quantum algorithm that keeps an internal state between answering queries. The same thing we can do for unitaries. There are two differences though. So first of all, pseudo-random unitaries have not been constructed yet, but that's none of our concern in this work. And we again can supply some form of the last row in this table, except that we only can prove that such a stateful simulation is possible in polynomial space. And we don't know anything about time complexity. Here's an example application. So one of the oldest ideas in quantum information processing is to basically construct money schemes from the no-cloning principle. And the most unclonable states are random states in some sense. So one idea is for the bank to just sample a random state and hand out copies of it as bills. And this is unforgeable and untraceable. This idea was put forward by Jilu and Song, and they instantiated it using their pseudo-random quantum states. What we can do now is we can instantiate this with the stateful simulation technique and thereby achieve unconditionally secure and untraceable quantum money. Here are some open questions. One question is, of course, can we simulate random unitaries efficiently? For now, we only know that we can do it in polynomial space. And one inherited question, of course, from Jilu and Song is, can we construct pseudo-random unitaries? So I consider this an important open question as well. This is the end of my talk. Here's a person performing lazy sampling, as you can see. Thank you very much for listening.
Good, thank you very much. So thank you to all the speakers, and we can open the floor now to the Q&A session. Okay, so feel free to, the panelists, you could share your questions on the chat to make sure it says your message will go to all panelists. The attendees, you could write your questions under the Q&A box. So there's one question there right now, and maybe I'll read this out, and you have some time to think about some more. So this question is to Jenna, and it goes as follows. In your first results slide, is the side information output Z classical? Is it okay to have it quantum? And V is a quantum verification procedure.
Yes, indeed. So V can be any quantum measurement with binary outcome. Z can be any quantum state, but it is essential that X is classical. Does that answer your question?
That's a question from Thomas Vidic, I should clarify. So Thomas, I don't know if you want to turn on your mic, Thomas, and add anything.
No, it's good, thanks.
Okay, we still have a couple more minutes. So we have a question from Niraj Kumar to Christian. Is there an intuition that random unitaries can be simulated efficiently by a BQP distinguisher?
Somehow, in my opinion, the intuition before our work was that neither of them can. Somehow because it seems like because you have these objects, like a quantum state, for example, is kind of a monolithic object. Right? With the function, with a random function, you're just revealing one output at a time. But with a quantum state, in principle, you're giving out the whole thing at once. So it seemed impossible. But it turned out that that was not the case, because one can, instead of handing out a random quantum state, one can maintain entanglement between the simulation algorithm and the distinguisher. And in a similar way, I expect in principle the case of random unitaries also to be possible. It's kind of a bit counterintuitive because it seems like I would have to look at the query. But in some sense, I'm also allowed to do that because I'm destroying most of the information by applying a random unitary. So I think these two intuitions kind of counteract, and I'm not completely sure because I haven't proven it, but I expect it to be possible.
Neeraj, did you want to add anything else? I think you're also able to speak now.
Yeah, it's good. Yeah, thanks.
Good, thank you. Ernest, it looks like you're there. Did you want to ask the question directly?
Okay, hello. This question is directed to Christian Majans. And this is regarding the full talk. Just perhaps a very basic question, but in the description of the simulator, you store the purifications of the previously generated states in the simulator, and you apply an isometry that extends them each time it's queried. Am I understanding that correctly?
That's right.
So why is it necessary to do this extension each time rather than just generating a fresh maximally entangled state, which seems informally that it would be hard random on the reduced states?
So what your suggestion would indeed work if I was giving out independent hard random states. But the goal is to simulate an oracle that samples a hard random state once and then hands out copies of it. And therefore,
okay,
yes. So what the distinguisher sees is kind of the normalized projector onto the symmetric subspace, and then you indeed have to, if you hold a purification of that state, you need to actually extend it to the purification of a bigger projector, the projector onto a symmetric subspace of one more copy.
I see. And the stateless simulator example that you gave, the main problem that occurs there is it's because the discretization just doesn't work somehow in this picture. Huh?
So somehow, I think why statefulness is required is kind of that we want simulation against arbitrary distinguishers. In particular, they are not query limited. We want that we remain efficient in the number of queries, but we don't know that number. So somehow, whenever you do a stateless simulation, you need to choose somehow an accuracy or something that determines the maximal number of queries, and that then you're already doomed.
I see. Okay, thank you.
Great. Or you've written a question. Did you want to ask Chris directly?
Sure. Okay, so I guess one of the advantages of state designs is that if you pick one of the states at random, say it's defined by some classical key K, you could give it also to others, and they could also generate the state as well, right? It doesn't need to be it doesn't need to be generated by the same entity. And once you have a state, this becomes more complicated. And I'm wondering if this is possible via some mechanism without communicating, right? That two people could, say, generate these hard random states and keep their own state so that globally it looks like it has the same properties as a quantum T design. Does that make sense?
I don't think that should be possible somehow.
So that's also would be nice. So you're saying maybe it can be proved to be impossible.
I think it should be possible. It should be we should be able to prove that it's impossible. Yes, because somehow in some sense, to extend this somehow, my suspicion is that our simulation method, at least the blueprint, the blueprint of keeping a purification of the mixed state that the distinguisher sees, that this is kind of that this is kind of the only method. This is my intuition, and if that's true, then I think it's impossible, because extending this purification is actually acts on all the copies.
Okay.
So in some sense, if one side hands out a couple of copies somehow, or applies that operation that corresponds to handing out a number of copies, then somehow the other side would have to act on their internal state to actually generate more copies. That's the intuition.
Okay, thanks.
Okay, so I see a question here in the Q&A box from Devdut Sharma. It's not entirely clear that this is the right session. Did you want to, Devdut, speak yourself, or I'm not sure if this is an accidental poster.
Yes, sir.
Yeah.
So
did you wish to ask
I
your
came
question?
to know that yes. Question is, there is no strict rigid boundary between classical and quantum behavior of particle, and especially I am talking about nonlinear concavity medium, nonlinear concavity, in which we realize the quantum state, but we using generally the photon for light reflection, but very macro, very weighted large glass sometimes show quantum behavior. I came to know only one or two paper in a conference regarding this. Means, is there any strict rigid boundary between quantum and classical?
Sorry, is your question directed at one of the speakers?
Means, in a nonlinear cavity research, quantum cavity, microwave cavity.
Yeah.
When we use the macro reflection glass.
Yeah.
I suggest we address this in the meet and greet room, which would be held after the session ends. Okay.
Yeah.
Dev. Yes.
Good.
We have 1 minute left. I'm just going to ask Omri a very quick question. So you said at the very end, so I'll wait till you switch on your mic. Yeah, you said at the end that you didn't have time to get into techniques. You have 1 minute. Can you get into techniques? Well, what's the basic idea? How do you do simulation?
What's the basic idea in 1 minute? The basic idea in 1 minute is to homomorphically, okay. So the most, like, the super oversimplification is that the way that the simulator uses the fact that it has the circuit rather than only having Oracle access to this verifier circuit is that it's going to use it and perform quantum fully homomorphic evaluation when the circuit evaluated is the circuit of the verifier. When you do it like this, you can make, when you have this ability, you can make the verifier give you its secret that it doesn't want to give you, like in a supernatural. Yes, because in the interaction, it sends this secret. It sends you a challenge, and if you answer the challenge, then it answers with the reward, which is the secret. And when you use fully homomorphic encryption, you have access to the circuit under the encryption, and under the encryption, it gets the correct secret and gives you the reward, everything under the FHE, and you know how to use this encryption of the secret in some additional way. Yeah. If it's I don't know if it made sense, but yeah.
So yeah, but it's still, I give you pretty harsh constraints. Okay, good. So we're 1 minute over. Let's thank everybody in the session again for excellent talks, and also for the entire day, I suppose. We're coming to a close. I believe there's still going to be closing remarks, so do stick around for that. Do have a look at the schedule. And otherwise, I guess it's meet and greet time, right? So that's it.
Yes, I think we will immediately proceed with the closing remarks, and then we go all together over to the meet and greet room for the last time. So yeah, Serge and I are gonna do this together, and we're gonna keep it very short, so don't worry. All right. Well, so this was QCrypt 2020 online. But as you know, after the conference is before the conference, and in particular, this case, this holds for us. But for you, this means that actually next year, around the same time, a little bit later, you can expect the QCrypt 2021. And we already know the dates, so those you can write down already in your agenda. I think I've also put them on the website. So August 23 to 27. And we really hope we will be able to host you guys in Amsterdam. But of course, it's pretty much out of our hands whether this will be possible or not. But we'll see. We'll aim at that, at least for now. Then a little announcement that was made in the business meeting, but here we go again. If you'd like to host QCrypt 2022, then please follow the instructions that we've just put online. So you should, there's a two-step process, and the first step is very easy. You basically just submit the letter of intent, specifying a few things to the QCrypt steering committee, and then you might be asked to work out a full proposal. But you can find all the information on the internet on the indicated website. Finally, we would like to hear back from you how you liked the experience, also of this online version. So we usually hold an exit survey or a post-conference survey, and it's being organized at the moment. We'll probably add some questions about the online facilities that we have provided, and we will send this out by email to everybody who registered, and probably also be available from our website. And we're really curious to hear from you how you liked it, how what did you use, what did you not use, because who knows, we might have all get used to having online conferences, and anything we hear of like how we can improve this experience, I think is useful to share with others.
So, and what's left for me to do is to say thank you to a few people. Well, we have to say thank you to many people, actually. So let me get started. First, I would like to thank our sponsors and supporters for their generous financial contributions to get this conference done. I'd like to thank the steering committee who have been sort of behind the scenes helping us through the entire preparation for this conference. Of course, I'd like to thank the program committee for putting together such a great program. Special thank you to the chair and the co-chair, Fred and Fai-Hu. And I want to give a very big thank you to our local support staff who have done an awesome job in supporting us. So that's Martine, Brenda, and Melanie from the UBA Congress Bureau who have taken care of all the finances and administrative issues. Susanne, who's done all the secretarial work. Jan, who has kept the website up to date on a regular basis. Esteban, who has done all the design for the webpage, but also for the meet and greet room. I think he has done an awesome job with this. Jelle, who has helped a lot with the help desk and the meet and greet room. Alex, who was responsible for social media, and Jana and Merdat for general support whenever we needed yet another hand to help. And I'd like to thank, of course, all the speakers, the poster presenters, the industry and sponsor exhibitors, and last but not least, of course, I'd like to thank you guys, all your participants, for attending the conference, and all the ones that are listening to this for staying till the very end of this conference. And with this, I'm officially closing this QCrypt 2020 conference. As already mentioned, you can still hang out at the meet and greet room and chat a bit more. And well, that's it. Again, thank you for coming and attending. And we're looking forward to hopefully seeing you in person then next year for QCrypt 2021 here in Amsterdam. Thank you, and bye.
I would also like to add a few extra thanks as well. So first of all, to everyone who's accepted to chair a session. This was very much appreciated. And a last bit of thanks, finally, to Chris and Serge, who've done a tremendous job organizing QCrypt. I think all of us, I think they deserve a round of applause, definitely. I think I speak on behalf of everyone here. Thank you.
All right. See you over there.
So speakers, please join us